continue to wander in from breakfast. I think there's a good crowd out there for breakfast. Should have a good tutorial here today. So welcome to the ESIG pre-workshop tutorial on weather data sets for power system planning. I'm very pleased to have John Zack here to chair this session, or chair the tutorial. I was telling John, I looked back at the original, or the first workshop we had on, I guess we called it forecasting, just plain old forecasting at the time, about 17 years ago, back in Minneapolis, St. Paul. It was in St. Paul. And the temperature that week in St. Paul never got above 0 degrees. And I was looking at the forecast for the temperature for this week and it looked like 99 degrees. It didn't say 100, it said 99. But I told John, on average, the temperatures for our workshops have been very nice. And John said, what's an average? So I'm going to turn it over to John.
Thank you, Charlie. And welcome to the tutorial, weather data sets for power system planning. Let's see. Yeah. All right, so we have our first issue of the day here. We don't seem to be responding to any of it. It should work from here. Yeah. Okay, sorry for that small technical issue. Weather data sets for power system planning. It'll be a 4-hour total this morning in 2 sessions. So the first session from 8 to about 10 a.m. Then we'll have a break. So we'll have 3 talks, kind of an overview of data sets. And then we'll focus more on specific data sets. First, the historical data sets in the second half of the session this morning. And then in the second session, which will be from 10:20 till noon, we'll look at the forward-looking data sets. And then we'll end with a 40-minute discussion period that will include a case study of using the data sets. So that's an overview of where we are going. So I'm going to start out with an overview talk on the state of the art in data sets. And we will first start out with a little bit of history. Where have we come from? And then the state of the art in 3 different areas, design and production, and examples of some issues with the data sets, data set evaluation and validation, and data set use. So all 3 of those areas are important in terms of where are we in the state of the art and what issues are there in each of those areas. So first, a little bit of history to provide a little bit of perspective. And this is a wind map from 1987 from PNNL and NREL, a 50-meter wind resource over the U.S. And this was created mostly with observations, surface and rain sound data, and then a basic elevation profile, a wind power law, if you're familiar with that, and surface roughness wind model, and terrain and land cover data, as well as some subjective adjustments. And we ended up with the wind map that you see there in 1987. So, that's where we were. And I actually do remember when this was the state of the art. So how many of you out there remember when this was the state of the art? Well, helpful. So I guess we have a very young group here. But as you know, technology has certainly evolved from where we were then. So there were no time series, there were no 3-dimensional data sets at that point for the energy applications. But now back to 2024. Where are we now? The state of the art in data set design and production. And the basic perspective is we have a time series of the three-dimensional states of the past, current, and future atmosphere. And you might throw in the Earth's surface and the oceans in some of these data sets as well. So now the state of the art is really some type of three-dimensional time series, over the globe or an area of interest. So how are these created? And the point here is there are a few fundamental types of approaches, and the flow chart on the right there kind of outlines, and I'm going to walk through that at a high level as to what are these approaches and what variations might there be. So there's an enormous number of variations within the types. There are a few main types, and then you can do a lot of different things and how you configure what data you use and so forth. And importantly, there's different attributes depending on how these data sets are constructed. And I think that's the takeaway here, that you need to understand the attributes of the data set you are using or maybe considering to use. So, and they depend upon how these data sets were constructed. So the first type here I'm going to look at is those that are directly retrieved from high resolution measurements. So the modeling here is minimal. Examples of this would be satellite-based sensors, the infrared visible sensors that you see satellite pictures, or radar is another example, perhaps not widely thought of, but you can certainly construct precipitation maps with radar. And this is the type of data that's closest to the direct measurement. So as you can see on the flow chart there, you use some type of retrieval model that transforms from the raw data that you measure to what you want to know. For example, surface solar irradiation, you measure satellite radiance in different channels. So that retrieval model does the work, and then you come out with usually a two-dimensional data set of the variable that you're interested in. And the advantage here is, of course, there are measurements with a minimum of modeling, other than the retrieval model, where there, of course, are some modeling assumptions there. But this is only feasible for some variables, solar being one, precipitation from radar would be another example. Over oceans, anerometers can measure the wind near the surface, so you can make a map of the wind that way. So, I mean, it is possible in a few areas, but solar would be the area where this is most widely used. And the example of this is National Solar Radiation Database, which is largely a observation-based data, a minimum of modeling, atmospheric modeling. And the important thing here also is that there's not assured that you'll have a realistic space-time correlations with other variables, as now you don't have consistent measurements, and you don't have a model that binds all the data together. So now if you take solar radiation from one data set and wind or temperature from another, they may not have consistent attributes. Now, the other side of the spectrum here is physics-based models with little or no sensor input. And the example here would be the climate models, which use climate parameter data like greenhouse gas information, as well as surface information on land use and elevation, land water distributions. And so you can simulate the past, future, or the current here. You're not limited by the period of record, as you would say for satellite measurements and data. You can only construct a data set for the period of record for which you have data. But here you can model as far back in the past, and people have, as far into the future as you're willing to make assumptions, right? So now you have a lot of flexibility, but one of the issues is that the model biases are not really constrained by data. You don't do data assimilation here. So now you have basically model data. Now, as I mentioned, you can do after-the-fact adjustments, but basically you're dealing with whatever the model physics will generate, right? And whatever assumptions went into that. And there are historical data sets from these models as well as the future. They're predominantly used for future states, and we call them climate models, as the CMIP6 set of data sets would be the example of that. So now we move into an area where we blend models with observations. and these are probably the most popular data sets, and they're constrained, to historical applications because you have to have observations in order to blend observations and model. So there's two main types here. One is what we will call an analysis data set, and this is based upon the operational weather prediction models. Every model cycle, they do generate an analysis that represents the state in the atmosphere to initialize the model. So you have ongoing upgrades to the latest technology in model physics and data assimilation, computing power, and you get real-time updates to the data set. But the minuses here are ongoing upgrades. So the system formulation changes over time. So what it was a few years ago is not what it is now, and it may have different attributes. So while this is the best possible data set created at the time it is made, over time, as you accumulate these data sets, have a historical archive, there are differences from the earlier ones to the later ones. Right, and the other important aspect here is assimilated data is limited to what is available at the time the data set is created, the analysis data set. So there's an operational window for each model. Whatever data comes in that window is used in the analysis. Whatever comes in after that is not used. So there's a lot of data that doesn't get into the analysis process here. So you have a more limited data set. So the two things here is you have a changing model data assimilation system, and you have a limited data set because of operational constraints. So in order to get around those two issues, reanalysis data sets have been constructed. And here we have an unchanging physics-based model of data assimilation system for the full period of record, right? So we get around that model of the operational analyses where you change the system. And the other part of it is the data used in the process can be all the data that is available, not just what is available in the operational time window. So you have a larger data set, as I indicated in the flow chart there. The historical sensor data is much larger than the real-time operational sensor. So you have more data and you have an unchanging system. Right, so those are the benefits of a reanalysis data set. And examples, MERIT-2, ERA5, so those are very popular and widely used data sets for power system and other applications. Now, a third part of this is secondary modeling, which is you use for downscaling or bias correction or other applications on the back end. So you can take any of these data sets, analysis, climate models, reanalysis data sets, and you can do a statistical or a downscale higher resolution NWP adjustment using a model such as WRF. So this can serve many purposes: bias correction, downscaling, optimizing for specific applications. But we have to be careful that you can swap out one set of model issues for another set of model issues, depending on how you apply the back end, right? So again, you have to do a lot of validation. So an emerging technology here is machine learning-based weather prediction models. And those are becoming much more active now in the community in the last couple of years. Many people are investigating these, and are actually these models that are usually deep neural networks that are the equivalent of the physics-based numerical weather prediction model. They're trained on data sets, usually analysis or reanalysis data sets. So they emulate the physics that are in those models. And there are some operational models already in production. ECMWF has one, some other operational centers too. And the advantage is, although the training time is long, the actual production of the forecast can be very fast, much faster than the physics-based models. And that opens the possibility that we can run very high resolution for some of these data sets, where there was a constraint on how high a resolution you could run a model to create a reanalysis data set or an analysis data set or a secondary NWP. It might be able to go a lot faster. So now some examples here of some not so obvious data issues in these data sets. So popular example here is ERA5, and through a lot of papers. There's one from Renewable Energy, a new champion of wind power modeling. So ERA5 is, in some sense, a reference benchmark data set, right? And this, you might call this state of the art, but certainly you can argue about that. And it has a number of strengths and weaknesses. The primary weakness is it's a relatively coarse resolution. It's global, at about 31 kilometers. And it certainly has a long period of record reanalysis here going back to 1940 and assimilates a large amount of data. So I'm going to show a couple of examples here of what can happen related to the attributes of the data set. So this example here is for an offshore site in the Mid-Atlantic. So I'll focus on the OCSA 0538 development track, and there's a nearby LiDAR measurement that was done for several years at Hudson North. So I'm going to use that for validation or illustration of observations versus the model. So, here's a typical data set evaluation, ERA5, LiDAR, 160 meter wind speed. So vertically, you have the ERA5 data every hour. So we averaged the LiDAR. LiDAR data was available at higher frequency in an hour, but we averaged it to be somewhat fair to the larger resolution model. So if you look at that, it's really good agreement. A negative bias, the ERA5 too low, about 0.8 meters per second in MAE 1.34. The overall agreement is fairly good, R squared about 0.9. Okay, so if you look at that, you would say, well, that's reasonable, and certainly not perfect. But if you look down in ERA5 webpage, item number 8, unknown problems, is something about data assimilation causing mismatch in low-level winds at the time of the boundary between the data assimilation. So if you look closer here, this is the average 1 hour change over the 24-year period, right, by month and hour of the day, right? So if you look at the 1 hour change, average of the absolute values, you'll see at the two data assimilation transition times, 05 Eastern and 1700 Eastern, you see a large change in the wind speed. And it's not the same throughout the whole year, concentrated in the April to June timeframe. So this is a problem. If you're looking at ramp rates in this data set, you're going to have this issue of very large ramp rates and whenever you use that transition time period. And actually, if you look at what's going on in the 12-hour data assimilation cycles, you'll see in the time right after the start of the data assimilation cycle, this is a comparison with the measurement data at the Hudson North site. You'll see large negative biases at the start of the cycle, and then the cycle removes a lot of that, and at the end, there's much lower bias, right? So there's a change in bias according to where you are in the data assimilation cycle, and then the transition between cycles causes that change. Now, if we compare that to the HER analysis, we see on the hourly wind speed data that they're not too different. The bias is somewhat similar. The MAE maybe slightly lower for the ERA5. So overall, you might argue maybe ERA5 is slightly lower. But if you look at the hourly data, hourly wind speed data, you can see 2 points here. Number one, the scale is the same on both, so it's a lot more orange and red on the HER side, and that means the variability is higher in the HER, pretty much at all times, which you might expect if you look at a 3-kilometer model versus a 31-kilometer model. But you also don't see the transition problem in the HER, right? It's a smoother transition between the hours of the day than it is in the ERA5. But now, you go back to the analysis issues, you have issues on the HER side. There was a major upgrade to the HER on December 2nd, 2020, and you can see the bias changed radically. If you look at before December 2nd, much bigger negative bias in the 160 meter wind speed, and after that, it's a much lower bias. Right? So you can see that from the point of view with height on the right there, and also in terms of hour of the day. So the general change, and this is what we mean about having an issue with a changing analysis system. But the ERA5 data issues go beyond the ramp rates. And another issue here is that the 84-year time series, if you look at this site, 0538 development site off New Jersey coast, you see what appears to be a decrease in the wind speed from the early years, 1940 to 69, to the late years. In fact, the lowest wind speed here is in the last year, year 2023. And so you might be concerned that, hey, there's a trend towards lower wind speeds in the Mid-Atlantic offshore. But if you look at the data in terms of the later years, 20 to 23 minus in 1940, 1969, you'll wind up looking at a lot of this is data assimilation related. And you can see the downtrend starts in 1980 when you tended to get high volume data sources like satellite data available. So much more data. And so the impact to the data assimilation cycle is a lot stronger in the later years. So that's the overview of the data sets and some of the issues. So I'm going to go over, since I'm about out of time here, and we'll go back to the next presentation, who's going to talk more about some of the problems in the data sets. And that'll be Justin Sharp, who is now with EPRI.
Thanks very much, John. And thanks for the introduction there. So I'm going to dovetail straight into John's stuff and sort of continue with talking about some of the things that are causing that create problems in the data sets that we've got. And John spoke to some of them already. And I'm going to sort of try and get into the weeds a little bit about why, but try and explain it in a fashion that is accessible to non-meteorologists. So the meteorologists in the room, this is all going to be stuff that's old hat for you. So just really quickly before I get into the detail, you will have seen this plot before, but I wanted to make it really clear that we have this evolving energy weather nexus that's really important that we understand, that we're going from a system that had some fairly significant weather dependency in the past, mostly on the demand side, to a system where weather dependence is extremely high, both on the demand side and the generation side. So this particular graphic starts at 2022 on the left and the right-hand side and converges to 2050, and is sort of representative of the amount of weather impact and weather complexity that we're developing on the system over time as we transition our loads to electrify them all. Essentially, we're creating mini residences on wheels that are electrified. We're electrifying all of our residential and commercial heating and cooling. And then we're doing that with a generation system which is fundamentally driven by weather. So the wind and the solar, which really explodes the complexity, which is why it's so important that we have really high quality data with which we can model our systems. This is just another representation of that, showing the complexity in a little bit more detail. I don't want to get into the weeds of this because it would take time away, but it's important to understand just how interconnected everything is and how related back to the environment it is. So John talked about attributes of quality representative data sets. Unfortunately, we have a TV screen that's flickering back and forwards here, so it's a little distracting. But these are the I've sort of I did a report for ESIG where we had a task force that pulled together all the ideas of what we needed out of quality data sets, and this is sort of a summary of what we came up with. There are physical requirements, relevancy requirements, and usability requirements. I'm going to sort of try and hit on a few of these today and explain why they can create such significant issues in our meteorological data sets. So they need to be representative of actual weather, that's obvious. They need to be coincident and physically consistent. So John talked about this a little bit with, for instance, NSRDB, which is a data set that sort of, it provides the state of the art for solar, but it sits on its own in that it's just produced for solar. So if you put another data set on top of it, you may not necessarily have that coincidence. You need to have sufficient resolution, which I'm going to get into heavily in a few moments. It needs to be chronological. We have storage now, so on the system. So the evolution of the weather from one hour to another is really critical in that. And then we've got these other attributes related to relevancy, having a long enough period, and then elements related to usability. These are all in the ESIG report, and you can go through them all in detail. And I want to sort of move on and talk about some of the consequences of this in a little bit more detail. This is there just for the purposes of this is a tutorial, so I think it's useful to have this information to go back to later, which basically summarizes that last slide. So today's data sets all have the following gaps. They have, and this basically goes through those attributes again, but in reverse. They have insufficient spatial or temporal resolution. They have insufficient time history. They have they're insufficiently validated, and their uncertainty isn't clearly quantified. Their distributions don't typically match with reality, especially for extreme events. They don't tend to all be physically consistent or coincident. Now, I'm not saying that every data set has all of these problems, but every data set has some of these problems. Many of them are archaic or not extended to the present date. They come from non-static modeling platforms. So John was talking about this with respect to the high-resolution rapid refresh data. That's an operational model that is designed to be as accurate as possible for producing a forecast. It's not designed to be as accurate as possible for producing a data set to be used for past conditions. And the care required for their use is not well advertised. So I know that I'm seem to be presenting a sort of doom and gloom scenario. I'm not. The data sets out there are amazing. This is really, really difficult stuff. But it is really difficult stuff, and it's important to understand the limitations of these data sets and that they're not observations. So going through the data that we have available today in a little bit more detail, since this is a tutorial, kind of getting into the weeds a little bit. So observations always provide the closest representation of truth. The problem with observations is that they're typically too sparse and they require rigorous quality control. They're often proprietary as well. So one of the things that I feel very strongly we need to change in our sector is we need to start sharing data. Every one of those wind and solar observations that are being collected by prospecting and by operational wind and solar plants is a jigsaw puzzle to seeing the big picture. And if we can get all the pieces of that jigsaw, we'll be able to produce a much better understanding of the state of the atmosphere and how it impacts our grid. And that's incredibly powerful for modern machine learning. So the ERA 5, I'm glad that John kind of beat up on the ERA 5 instead of me having to do it. Again, fabulous data set, but it is not the bellwether for renewables integration type studies that it's been made out to be. It's incredibly coarse, and I'll show you the results of that in a few moments. Then you've got the Wind Toolkit, which is a 2-kilometer data set, which is the opposite of ERA 5 in many of its issues. It has a high enough resolution, and again, I'm going to show you some examples of the impacts of resolution in a moment, to be able to resolve most of the physical phenomena that are relevant to the grid. And it includes a forecast database, which provides a representative look at how well we could forecast ground truth, which is important for power systems modeling. But the problem with it is that it only modeled 2007 through 2013. It is being extended, but it's been extended in a very ad hoc way. It's not, there's no sort of well-planned, well-budgeted method for its extension. NSRDB is actually a higher resolution than 4 kilometers now. But it's based on satellite observations. It was that first example that John showed. It's a continuous and consistent data set since 1998, so we want that. That's a great attribute. But it wasn't originally designed for integration studies, and the non-solar fields that are in it are misleading interpolations of MIRA2. So MIRA2 is a reanalysis data set that has found its way into NSRDB. This is in the documentation if you read it carefully, but the temperature data and the wind data that you're seeing in Mirror 2 is not of a quality that can be used for integration studies. It's very low resolution. But it's interpolated to 4 kilometers, which makes it appear as if it's high resolution. Then you've got the high resolution rapid refresh. As John mentioned, that's an operational model. It's a fabulous model, but it's not designed for long-term, for its use as a data set to describe the long-term variability of the atmosphere. It's an operational forecast archive, and so the model configuration is inconsistent in time. And then lastly, data from proprietary models often is opaque and often I found has limited scientific basis. So the common issue amongst all of these data sets is they lack validation and an examination of their use case applicability. And that's the stuff I'm going to talk about in the second half of the presentation. So this is a summary of all that for the data sets that are available or were available a couple of years ago. We want ideally everything in this table to be dark red, dark green. The dark red is where we have really big gaps. Anything that's not green, we have a gap. So you can see there are lots of gaps in the available data sets. So let's dive a little bit deeper into understanding grid spacing, what is commonly known as resolution. So this pretty picture here is close to where I live in just outside of Portland, Oregon. It's the Columbia River Gorge. It's a gorge through the Cascade Mountains, looking west to east in the big picture, and the other picture looks east to west. So you can see there's a lot of topography. Downstream of this gorge is about 6 gigawatts of wind energy. And the gorge is the thing that drives that wind energy. So I'm going to show you why grid spacing is so important. So this is how these synthetic weather prediction models work. The category that John was talking about, other than the physical models where we're doing synthetic numerical weather prediction using physical processes that bring together a lot of different observations. So John described that process of taking the observations and moving them onto model space. The terrain map on the bottom left basically shows the topography at a sort of essentially a full resolution, the highest resolution available. This is kind of what models often see, particularly like the ERA 5 model. That's kind of how the topography looks. Here's kind of putting the glasses back onto that. So I'm going to show you that in a bit more detail here. So this is USGS 15-second topography of this region. So you've got on the left-hand side, the Northwest, on the right-hand side, zoomed into the Columbia River Gorge, and I've shown you where the wind farms are and where the 2 pictures were taken. And you can see that with high-resolution topography like this, you can see all the drainages, you can see the mountain very clearly. This is Mount Hood in the, let's see here, does this work? Yes, it does. Mount Hood right here. Columbia Gorge right here. You can see the higher mountains on both sides. When you go down to a 1 kilometer grid spacing, which is what the highest resolution numerical weather prediction models use, you can still see all of those features in the topography. And so you're able to capture and model them relatively well as physical processes. This is what that looks like at 3 kilometers. So now you've gone to the grid spacing of the HER. You can see we're already kind of blurring the picture. And when we zoom into this region, the mountain here, Mount Hood, is kind of essentially, we go back. Oops, too far. Oops, going the wrong way. So this is 15, this is 1, this is 3. So even at 3, we're losing the ability to resolve this topographic feature of a gap that's been created by the river. We're losing the taller mountains. We're losing the fact that this is a canyon. And we're creating other ways for air to move from east to west or west to east. When you get down to 9 kilometer grid spacing, which is what the most operational models use, you can really see how you're losing that ability to resolve the topography. You just have some high mountain here and some high mountain here, and like a very broad pass. When you get down to 30-kilometer resolution, this is what the ERA 5 data set that a lot of people are using. This is how it sees that region that has over 5 gigawatts of wind. There is basically no real sense that there's a gorge there. And if you don't resolve the topography, you can't resolve the features that that topography creates. And so what I've shown here in this plot is how, if you look in a vertical cross section, what this would look like. So that at 3 kilometers, you're actually seeing these mountain peaks and valleys across section. Whereas when you get to 27 kilometers, you basically have a mountain. So the model knows there's a mountain range here, but it doesn't know really much else other than that there's a kind of saddle in this region right here. And so I want to show you what the differences are of this. And I went to a great deal of effort over the weekend to put together this animation of the the ERA 5 data set versus a high resolution run of the same model. So this is some work that I did when I was at Iberdrola Renewables. All the way back in 2010, we were looking at this region at 1 kilometer resolution with NWP. And then on the right-hand side, you have what the HERS represent, the ERA 5 representation of this same phenomena is. So you can tell that those two are entirely different, right? They don't even look vaguely the same. They're exactly the same time, and they both come from a numerical weather prediction model. The only main difference is that one has 1 kilometer resolution and is resolving the topography, and the other one is not. So you can imagine if you were to use this data to predict your wind generation from all of those wind farms, you're not going to get the right numbers. And this is really important for people to understand. So I'm going to show another example of this, and sort of again, really hitting this home. So we need to have spatial and temporal scales that are relevant to the system that's been modeled. And so this is the Bay Area in California. San Francisco is up here. This is the Bay. Altamont Pass is in this region right here. And so this uses some output from the GFS model. It's not hard to find these examples. They're everywhere on an almost daily basis. This is the GFS model, which is, I think, rough. At the time when this was done was, I think, roughly 12 kilometers in resolution. This is the NAM model, the North American model, which is higher resolution. And then this is the high resolution rapid refresh. These are all operational models of the same thing. So we talked about concurrency and physical consistency. And then we also talked about providing a 30-year update in the time series. The thing I want to hit home here on this particular slide is how these three outputs are from exactly the same time. And if you look at this region here, you've got much cooler air in the GFS model than you do in the, much warmer air in the GFS model than you do in the NAM model and than you do in the HER model. So what you can see is that the marine air has penetrated much further into the Bay and into the San Francisco area than it has in the lower resolution models. And this is impacting the amount of wind energy that's being produced over here in the Altamont Pass area. It's also likely to be affecting the cloud field over this whole region here, where there's tremendous amounts of distributed solar. So you've got all three impacts on this one picture that are different across different models. You've got different amounts of solar irradiance, which is going to impact all your distributed solar and any commercial and utility scale solar in this region. Then you've got differences in how the wind field is being handled, which is going to impact your wind generation. And then you've got differences in your temperature, which is going to impact your load. So all of the environmental variables potentially are much different between these different model runs. So I wanted to really make it key that model space is not the same as observations. You need to understand these differences when you're using it, because otherwise you've got a garbage in equals garbage out situation. So I sort of posed some of these questions here. You know, you have 50s, 60s, or 70s. Which one's right? You have light, moderate, or strong wind in the ultimate area. Which one's right? Is it cloudy or is it sunny in the Bay Area? These are all questions we need to answer before we use this data, and we shouldn't necessarily assume that the high resolution data is the best, because it isn't always. So to do this, we need to validate according to the use case. So a use case that I like to talk about a lot is that of resource adequacy, because it's the easiest to get our heads around. We think about the fact that we need to know what our wind generation is, what our solar generation is, what our loads are, in order to be able to assess where our risks are. So I did a fairly simple study of some data in the Bonneville Power Administration area, because their data is available. Their generation data from wind is freely available, and I validated it against these synthetic data sets. And what I found was that there were certain weather patterns that had significant biases, where the model would overpredict the wind energy. I also found that those exact same periods where the model overpredicted the wind generation were periods of high loads, because it was very cold or it was very warm. So you have a double whammy that the model is behaving poorly at a time when you've got the most risk. So these are the kind of questions we need to be asking ourselves when we're using these data sets. And John pointed to similar questions. We can't just use the data as if we're assuming it's perfect observations. So the last slide here, because I see I'm over time, is on that validation and uncertainty. As I mentioned before, comprehensive industry-wide transparency of data sharing of our meteorological generation and availability data is the key to unlocking the door with respect to, first of all, understanding how good these data sets are and where they fall over and what the downstream consequences are, but also to adjusting the data sets and making them better. And essentially, we've got jigsaw pieces scattered over the table right now. We need to bring them together. And this is the low-hanging fruit that's not difficult to do if we can all just cooperate with one another. ERCOT has started to do this, and I think the other ISOs need to do it as soon as possible. So I was going to talk a little bit more about this if I had time, but I don't. So the bottom line is it's complicated, and I'll leave it there. And thank you. I should just mention that that all of this work came out of a report that's available on E6 website.
Well, thank you, Justin. I think you raised a lot of questions. I have a few I know. I imagine the audience might as well. But to stay on time, we'll defer that to the discussion at the latter part of the second session this morning. We'll have time. So remember all your questions. So we'll move on to the next presentation. Our next presentation will be the evaluation and adjustments to the ERA 5, and Jim Wilczak, who is a research meteorologist at NOAA. Jim?
Great.
Sorry about that.
Okay, thank you. I assume you could hear the first statement that I made, but I'm going to continue on the same theme that John and Justin have of kind of criticizing the ERA 5 reanalysis a little bit, but I'm also going to show that you can correct many of the errors. And my emphasis in this presentation is going to be on looking at extreme events in the ERA 5, especially wind and solar energy drought events that happen on longer timescales. And if you're interested in more of the details of the presentation, then I can go cover this morning. You can find them in this recently published manuscript. So John already covered a lot of this, so I'm just going to skip through this first a couple of points. Other than, I guess I would say, why use a reanalysis? And one of the advantages of a reanalysis data set is that it covers many decades in time. And so if you're interested in an extreme event that by definition happens very infrequently, you may need a very, very long data set in order to be able to get sufficient statistics of those infrequent events. Yeah, so the ERA-5 reanalysis, again, one of the reasons that it is used so frequently in the community is it's considered one of the best that are out there. And John already mentioned this article, hailing it as a champion for wind power modeling. And I put quotes on this champion. So we'll look at some of the problems that actually exist on it. And so one of the biggest limitations, of course, of the ERA-5 is 31-kilometer resolution that was mentioned previously. But of course, you know, if we end up having to build in the future 8 or 10 times as much wind capacity generation than we have today, maybe that's not such a problem because we're going to be having wind turbines popping up everywhere. So I don't know, that's a point for discussion that I think we could have. In any case, the observations that I will be using in this talk are hourly values of 100-meter wind speeds together with surface temperature and pressure, and then the direct and diffuse irradiances. And so the overall goals are to evaluate the accuracy of the ERA-5 for wind and solar energy, but not just in a mean sense, but also looking at the extreme tails of the distribution, looking and especially at wind, drought, and flood events. And if the ERA-5 is not sufficiently accurate, can it be corrected? And then the third point is to develop some metrics and tools that would be useful for evaluating not just ERA-5, but any reanalysis data set for wind and solar extreme events. So the observations that we use for solar are shown here. The emphasis is placed on the quality of the observations as opposed to the quantity. We require good metadata for each of the sites that we use and observations that span a full year. For solar irradiance, we have 41 observation sites that come from the NOAA SURF-RAD and SOLRAD networks, shown as the red dots in this map. There's 13 of those. And then in the red box, there's the DOE ARM SGP facility with 28 sites there. I chose these data sets because of their high quality. They require frequent cleaning of the sensors. The sensors are heated to minimize impacts of snow and rain and dew. I then take hourly values of the irradiances and create power from them by using the DOE Sandia PV Lab software, assuming that the solar panels are optimally latitudinally dependent, have latitudinally dependent tilts, include wind speed and temperature dependencies, and then I average those hourly powers up to daily values. And I will focus a little bit next on the observations from this Penn State University site, PSU, shown in the top right there. And turning now to those PSU observations, I'm showing here now simple scatter plots on the left of the diffuse horizontal irradiance. And you can see that the ERA-5 has a pretty significant low bias of the diffuse. And the middle panel shows the direct horizontal and irradiance. And you can see that in contrast, it now has a high bias there. And if you sum the two of those together, those two opposing biases tend to cancel one another out, and you actually do a pretty good job of getting the global horizontal irradiance. But of course, if you have solar panels that are tilted towards the sun to make to optimize the amount of energy that you produce, you're going to be making more use of that direct beam and less of a diffuse, and you would expect to see a high bias in the solar capacity factors. And that is shown here in this plot, where the left is the scatter plot of the ERA-5 versus SURF-RAD PSU site solar capacity factors. And you can see that for overcast conditions, the ERA-5 actually does pretty well. And also for completely clear sky conditions, it does pretty well. But for these mid-range values that include partly cloudy conditions, the ERA-5 is biased high. And the right panel shows the annual cycle, where now the observations are in the red curve. The dark blue curve is the ERA 5 averaged each day of the year over this time period from 1998 to 2022. The cyan and the yellow curves are 4 harmonic fits to that data. And you can see that the ERA 5's biases are really constrained to the cold season period of the year, the worst in the winter, and during the summer months, they almost disappear completely. So can we correct those errors? And to do this, I use a technique called quantile correction. Basically, what you do is you just sort all of those capacity factor values from the lowest value to the highest value, and then you present those here as a scatter plot. If the ERA 5 was perfect, the data would all fall along the one-to-one line. You can see it does not in the blue symbols there. And so then what I do is calculate for different bins of the ERA 5 data, multiplicative bias corrections. And after you apply those, you end up with the purple data that now does fall along the one-to-one line. And because the ERA 5 has seasonally varying biases, I have to do this separately for each month of the year. The left panel is for January and the right panel is for July, when the ERA 5 does much better. So how consistent are these errors across the entire domain? So I've taken now, I've calculated these quantile plots for each of the NOAA SUP3rCC and SOLRAD stations and plotted them here in a geographical sense with the northern sites along the top and the eastern sites on the right. And you can see how consistent the ERA 5 errors are at all of these errors, in these, including for the ARM aggregate, which is down in the middle panel of the bottom row. So these errors really are very consistent, making them potentially much easier to correct. Looking now, going back to the PSU site and seeing what the impact is of these corrections. The top row of figures here is the raw ERA 5 compared to the observations. The bottom row is the bias corrected ERA 5 compared to the observations. The left panel is the annual cycle. You can see after applying the quantile bias correction that the annual cycle agrees almost perfectly for every month of the year. The middle panels show that after bias correction that the ERA 5 BC is unbiased, and the right panel shows histograms of the ERA 5, orange being the SUP3rCC, light blue being the ERA 5 values, and after bias correction for the December, January, February time period shown here, you can see that the histogram agrees almost perfectly. So if one of the main points I would say that I'm really concerned with or most motivated to look at here is the ability of the ERA 5 to be able to replicate wind and solar energy drought events. And one of the tools that I'm using to evaluate that for that purpose is what are called drought intensity duration curves. And so basically what you do is you take the time series of solar power. I do a running mean through them using windows of different lengths from 1 to 90 days duration. And then I find in that time series the single worst event of lowest power or highest power that occurs over the entire time series. And then I express that power as a % of the annual average. And that's what's plotted here. The bottom half of the figure are now showing wind drought events. The top half are showing flood events. The blue curve is for the ERA 5 and the red curve is for the observations. And what you can see is that the ERA 5 consistently overpredicts the amount of energy that's going to, or amount of power that's going to be produced during these worst case drought events. And for some durations, it can be off by as much as 50%. So that's pretty significant. And for flood events, it produces too little power. After you apply the quantile bias correction, you can see that the ERA5 actually does now a pretty good job of being able to predict these worst case flood and drought events. So what's the spatial consistency of these intensity duration curves for these worst case droughts? You can see that here. Again, for all of these different Sup3rCC SOLRAD sites in the ARM aggregate, and at every location across the US, the ERA5 overpredicts the amount of energy that's available during a flood event. In some cases, many cases here for some durations, again, it's bigger than 50% error. And after you correct it, it looks like this, much better. I'll just toggle back and forth, before and after, and you can see that it's improved by quite a bit. So up to this point, I've been using daily average values in order to correct the ERA5, but you may be interested in hourly values. That's much more common. And so the question is, can I now use these daily value bias corrections to actually correct hourly values? And the basic assumption that, well, what I'm going to do is just take those corrections and apply it to the hourly values and see what happens. And the basic assumption here is that the deficiencies, the radiation deficiencies in the ERA5 are independent of the sun elevation angle. So if you make that assumption, now here in the plot, what I'm showing is hourly values in this quantile plot. Again, this is for December, January, February. The blue curve is for the raw ERA5. You can see again in the hourly values, it has this problem. After you apply those corrections, you get the red curve. And although it's not perfect, it agrees much better with the one-to-one line there. So wind observations for the evaluation that we use are shown here. There's 157 sites, most of them tall towers, many of them from the WFIP1 field campaign shown in these two blue boxes. We had I used 16 LiDARs, 3 of which are from offshore floating, 14 SODARs. For the wind observations, the towers, we required booms on opposite or orthogonal sides of the towers to avoid tower shadowing. We checked for icing conditions. Some sites within extreme topography, like in the Columbia River Gorge that Justin talked about, I excluded because I knew the ERA5 wouldn't do well there. And then we used the wind toolkit power curves to convert the hourly wind speeds to wind power and included density. And I'll talk a little bit more next about the RMSGP data in the center there. Yeah, and so what we found is that the ERA5 has a low wind speed bias by up to 1.3 meters per second. In the left panel in the annual cycle, you can see that that bias is independent of the season of the year. The middle panel shows the diurnal cycle. The bias is independent of time of the day. And the right panel is a simple scatter plot of daily wind speeds. And you can see that it has a low bias and a slightly too small slope, which suggests linear regression correction could work. And how consistent are those biases? So here I have a map showing each of our observation sites. The two large circles in the middle are these aggregates of 97 and 27 tall towers. You can see across the central part of the US and even in the western part of the US that the ERA5 is very consistently biased high. This includes the 3 offshore sites that are used also, which John had mentioned the bias there. The only difference is in the northeastern US where there's a more even distribution of data. Yeah, so quickly, I think I'll just move here to the right panels of this figure where I now show the impact of the bias correction on these drought intensity duration curves. The top right panel shows the raw ERA5. Now, in this case, for wind, the ERA5 greatly underpredicts the amount of wind power that will be available during these worst-case flood events. After bias correction, although not perfect, you do much better. And if you look at the distribution of this across the entire US, again, it's a very similar story. Each of these panels is groupings of these different sensors shown in the map here. And again, yeah, the errors in the error 5 are pretty obvious there. And after applying the linear bias correction, you do a much better job on these wind and solar energy drought events. So in summary, I'd say that the error 5 derived solar capacity factors, we see that they've been biased high by about 25% in winter. On average, the wind capacity factors are biased low by about 20%, so in opposite directions. We've seen that these intensity duration curves are, I think, a really useful tool for trying to be able to understand these extreme events. And they show us that the error 5 produces too much solar power during solar droughts by up to 50% and too little for wind power. In many locations, the quantile correction for solar and the linear regression for wind provide unbiased estimates for the for solar power and wind speed, and they do a much better job on the wind and solar drought events. And I'd like to end perhaps with just a question that I don't have the answer to, and that is what magnitude errors are in fact, or would be acceptable for use in a capacity expansion model? When do we say that good enough is good enough? Obviously, these 50% errors of solar in one direction and 20% of wind in the opposite would be unacceptable. But how good do we have to get? I don't know. So I'll stop there. Thank you very much for your attention.
Thank you, Jim. I think we have time for one quick question, and we'll certainly have more time at the end of the second session for discussion and questions. So anybody have a fast one here? No, okay. We'll move on and we'll come back at the end of the second session and talk further. So thank you, Jim. So our next presentation, and we'll move on to the next segment of the tutorial, which is approaches to historical data sets. And next presentation is POTUS 404, a high resolution hydroclimate data set. And the presenter is Sue Haupt, senior scientist at the National Center for Atmospheric Research. And we'll need the microphone back there, yes.
Okay,
Right.
is that about right? Yep.
Yep, so
And
you're
is there a
sitting here
point?
to,
Great,
Joel?
thanks. I must admit that first my colleague Andy Newman was invited to give this talk. He was not able to attend this week. I happened to sit right next to him in office space at NCAR, so I got nominated to give his talk on his behalf. So fortunately, Andy and his colleagues have given me the data. I was very aware of their project, and they have built this data set that's 40 plus years at 4 kilometers. Now, they are hydrologists. We have a very active hydrometeorology group in the Research Applications Lab at NCAR. They care about precipitation and its impact on, droughts, floods, all the things Jim just talked about. So they were focused on trying to get the water vapor transport and the precipitation correct, so they could then take the resulting data and use it to feed, the hydrology basins across the United States. So when we talk about years that they did, they're not chronological years, they're actually water years. So when you see WY, it really is water years. A water year is defined as beginning October 1st, and then going on through the following end of September. And the idea here is they get the snowfall and melting correctly over the course of the particular water year. Now, this began, we just heard from Jim all the issues with ERA 5. And it begins with the assumption that most of those biases are due to bad resolution. So they needed to come up with being able to downscale ERA 5 with a much higher resolution model. And they chose the weather research and forecasting model built at NCAR, used across the world, specifically version 3.9.1.1. They use the ERA 5 initial boundary conditions as well as the sea surface temperature. That is available at 3 hours. They also use spectral nudging within the domain. Recall that ERA 5 already is a reanalysis, so it integrates some of the best observations available in the world. Now, if you want to read more about this data set, read the paper by Roy Rasmussen, led by Roy Rasmussen and Fei Chen at NCAR. I am not a co-author. You'll see here that Andy is a co-author, Andy Newman. So is Lulin Xu, who just prepared a major tutorial for the sponsor, USGS, about a month ago, and gave me all his slides, way too many slides. And Tim Schneider, also a very good colleague who manages the project, helped facilitate getting information. Now, we have heard about the issues of topography. Justin made that really a big deal. I love this plot that you see on your right, where you can look at the resolution at climate scales. The mountains totally disappear. It begins at scales at about 2 kilometers and goes down to climate scales. So as Justin made the point, if you don't have those mountains represented appropriately, it means you don't get the correct wind, water vapor, cloud transport over those mountains. You're going to get wrong answers. So, of course, it really makes a difference for water vapor transport, but also getting the wind correct in those mountain valleys, as well as the precipitation. If you don't resolve it, you're not going to get those details correct. It also impacts the wind and solar irradiance as well as temperature. Now, this group, as I mentioned, cares more about the hydrology, and they've done a lot of effort in validating for hydrological purposes. One of the things they really claim to fame of this data set, it produces mesoscale convective systems very appropriately. Now, they provide about 30 to 70% of warm season precipitation. One of these is the simulation, the CONUS 404, the other satellite. Which do you think is which? Anybody want to make a guess? Okay, so the simulation is on your left, satellite is on your right, and it is amazingly good at getting these MCSs, the simulation, the transport of the weather systems across the US. But note that optimizing for water vapor transport, we expect will also optimize for the variables we care about for renewable energy. Now, temperature, of course, they have done some very good analyses for. Those of you who care know about NWP, because they care about clouds and getting the physics right. They use the Thomson-Eidhammer microphysics developed at NCAR. They use Yonsei University planetary boundary layer, RRTMG, radiation schemes. It has 51 levels considered good for a reanalysis like this, 4-kilometer spacing. That means it's convection permitting. We don't have to parameterize the convective variables. And they've done reanalyses over the years. This one is best than the last CONUS one. Here we're looking at the 2-meter temperature, comparing it to the PRISM observational data set, considered one of the best observational analyses, where you're basically trying to grid all the observations available. And we see that we have improved on the last version in terms of temperature. Now, they have validated for solar radiation, and they validated against the National Solar Radiation Database, developed by NREL. Not a bad one, but we have heard about some of the issues. The nice thing about this is it's available on the CONUS 404 can be downloaded from NCAR's research data archive. And there's I'll have on my last slide this URL again. So this is freely available. It's made for the community. They use in the lowest 1 kilometer, they use 50 to 100 vertical meters, for wind energy applications. Sometimes we go finer than that, but for the hydrological uses, this is what they chose to use. We look at the solar radiation. If you actually had the National Solar Radiation Database, it would look very similar. But when you do a difference, like on the bottom plot, you'll see that there is a high bias. And that's not surprising, because when we look at clouds, and this is a well-known issue in WRF, and this is a comparison, we end up with a low bias on clouds, so which leads to a high bias on solar radiation. This is a comparison with MODIS. That's MODIS is mounted on a satellite that passes through twice a day. So we only have twice a day observations. We have that since 2002. It's actually at higher resolution, so that had to be coarsened to compare to the CONUS 404 over the same period. Again, we see that there is a low bias on clouds, which explains the high bias on solar radiation. And as Jim just pointed out, they don't actually have this, but when we've done WRF analyses in the past in our solar projects, we find there is a seasonal and diurnal signal to that. And if you know that, you should be able to correct for it. So on clouds, you see in the summer, in particular during the day, we have very high biases in the southeast United States, up to 19%, less so in the Mountain West. It's a little bit better in the winter than it is in the summer. And of course, because it's satellite, comparing to satellite obs, we can get night biases too on the clouds, less important. Now, they haven't done as much validation for wind energy. Out of the BAMS paper, they did look at a comparison with profiles over the 42 years in terms of differences from soundings, atmospheric soundings that are put up twice a day, in terms of differences in temperature, relative humidity, and wind speed. And, on the left is at 12 UTC, on the right at 0. This is really hard to read. So let's focus in on the Midwest. It's validating against soundings at those red points in the Midwest. They're actually kind of northeast as much as Midwest. And you'll see that it goes up to 10 kilometers. What we really care about for wind is the lowest couple hundred meters. And that's where the biggest bias is, unfortunately. So in fact, we end up, I thought I had a, with a 2 meter per second bias, positive bias for wind in the boundary layer. So again, we have not totally corrected for that. Possible to do more analysis. Also, if you can figure out where some of these biases are coming from, one should be able to use some sort of machine learning to correct the biases on a, a daily, monthly, whatever type of cycle you want. Now, Justin did a really nice plot comparing different data sets. The group who did CONUS 404, again, these are hydrometeorologists, looked at comparing to other available data sets in terms of all these different variables in terms of realism of climate variability, biases, diurnal variability, homogeneity, and on down, record length, future projections. On the left part of the plot are the observational data sets. And you'll see that they often have fairly long, especially, for instance, PRISM has rather long observation lengths. And when you get to climate models, they're very long, but they're very coarse. And the idea is when you look at CONUS 404, it has more green, which is what is called good performance, than the other data sets. Where it's missing is yellow on biases. Yellow is medium performance. It still does have some biases. Record length, it's not where the climate models are. And it doesn't have full future projections. However, they are in the midst of doing pseudo-global warming simulations to get the equivalent of those projections. So what the heck is pseudo-global warming? Okay, what it does, the PGW is some control that shows historic climate, and then a delta that looks at the difference between the projection into the future and the historic climate. So the idea is you have to use the same radiative forcing scenario on both the projected and the historical, and they have to be long enough so that an average is applicable. And generally, we consider about 30 years to be long enough, or you can use ensemble data, lots of model runs with some perturbation to get that. Now, some of the pros and cons of pseudo-global warming compared to the direct downscaling from the global climate model. Okay, so pseudo-global warming, it's a reasonable cost. It doesn't take as much computer time. All of these, the CONUS 404 took a year to produce on USGS's Cray supercomputer. So getting 40 years worth of data takes a lot of computer power. So we have to be reasonable here to get another similar, 40 years. It is representative of the ensemble mean. It captures the general signal, the change. It doesn't have these internal variability issues that the direct downscaling has, and it's not impacted by the GCM biases. Often downscaling is totally dependent on the biases in the GCMs. The CMIP6 GCMs tend to run hot in general. It, however, on the con side, does not capture systematic changes in weather patterns, and that's one of the strengths of the direct downscaling from the GCMs. But it also doesn't represent climate change variability and uncertainties in the ways we would really like. Okay, so what does this mean for our data set? This, we have our equation. So the control is the downscaled version of ERA 5 that we were just talking about. The delta, it looks at the projected and the historic that, over water years 2022 to 2063. To get those, we use NCAR's large Ensemble Community Project. So the LENS 2 data set. And what that is, it's a 100-member ensemble of NCAR's Community Earth System Model 2, one of the climate models used for the CMIP projections. And it's actually less biased than many of, all the CMIP 6 tended to run hot. CESM 2 was a little bit less so than some of the others. We have to use the same shared socioeconomic pathway, projecting what are the assumptions into the future for CO2 forcing. And this chose scenario 3, SSP 3-70. So the equation looks like this. The downscaled version of each of those. So let's look at what that means in terms of temperature change. We begin with the CONUS 404, the actual downscaled from ERA 5 that we began with. We saw some temperature rise between 1980 and 2020. Then we compare to the LENS 100-member ensemble that runs out to 2065. We see that it, again, was a little hot on temperature. So we take that out into the historic, out to 2020, versus the projected beyond that. Take the years 2022 to 63, move that back. And what would that be if it were run concurrent? And we see it would actually be a lot higher due to global warming. So we look at the difference between the CONUS 404 and the LENS ensemble and look at that delta, move that delta up to the pseudo global warming, and then that correction becomes our pseudo global warming data set. Now, this whole data set production is in process now. As of about a month ago, when Lu Lin made this slide, they had 37 years. They were going to do another 5, so I suspect there's another year or 2 done since then. They had some preliminary plots they used for the tutorial that they made the data set. On the top, we see temperature, bottom precipitation. Left is historical. That's basically the downscaled era. And the pseudo global warming is in the middle. That's what that data set would have produced if we had global warming over the 1980 to 2020 years. So it's just a correction due to the global warming expected in the future. And the difference data set is on the right. As one expects, we see that there has been an increase in temperature that was built into it, and the impact on precipitation is on the bottom. Also an increase in precipitation in most places due to this pseudo global warming. So in summary, we do have this CONUS 404 data set. It's 42 years. They are continuing to run it to keep the simulation near current. So there will be new years coming out. It's based on the Weather Research and Forecasting model. It has ERA 5 initial boundary conditions and SST with spectral nudging. It produces hourly 2D surface and 3D fields, roughly 50 to 100 meter vertical spacing. You see the URL to download these data there on the right, and there's true intention to keep that available. We may have reasonable wind speed performance. We did have a high bias on solar, and that pseudo global warming analysis future data set is in process now. So any time for questions?
Thank you, Sue. I think we're a little tight on time, so we'll defer the questions to the discussion period at the end of the second session. And we'll move on to our next presentation now, which is applying the wind toolkit and WTK-LED through grid integration is given by Luke Lavin, a researcher at NREL.
Great, thanks, John. It sounds like this is on, so I'm going to assume folks can hear me. So I am, yeah, we'll go with the next one, yeah, and then just use the arrows. Excellent. We don't have a pointer or anything like that, right?
We do not.
Okay, let's go. Great, so like John said, I'm Luke Lavin. I'm a research engineer at NREL, and kind of like Sue was saying earlier, I've got a couple of other colleagues, mainly Carolina Draxel, who some of you may know up at the wind site at NREL, and then also my colleague Greg Brinkman, who were invited to give this talk, but somehow I ended up with it. And then also thanks to a number of other folks and to some of our workshop participants from a few months ago earlier this year, including Justin, John, and a bunch of other folks in the room. We'll sort of share some of what we learned there as part of this talk as well. So I guess folks have already kind of said this, but I'm sort of more on the power systems side than on the atmospheric science side. And what I see when I chat with folks in the field is that we have this growing need, just like Justin's figure was showing, for more high quality resource data for power systems applications, both in the present and especially looking into the future in these systems that are more dominated by variable generation. So this is sort of also from Justin's book, right? We have this new data set. Really, it's data sets, as you'll see on a couple of the subsequent slides. The update to the Wind Toolkit, which is the Wind Toolkit long-term ensemble. I feel like it's really data sets that cover many of the usability requirements, but certainly not all of them that Justin laid out. So sort of like we were saying, there's really just never a perfect data set. But at the same time, the hope is that this new data set that we'll be talking about in a sec here is representative of actual weather, is sort of physically consistent, is at least for a few of the years at 2-kilometer resolution, chronological, and as you'll see is available online for download and hopefully for use with some of your tooling and modeling that has used the historical Wind Toolkit over the years. Now, at the same time, if you remember sort of when the historical Wind Toolkit came out and you looked very closely at Justin's chart, there was a big red no on the sort of extension of the data set on some kind of regular interval. So that is still a concern on our end, right? And part of what we want to lay out in the second part of the talk today is sort of what we're doing at NREL on the validation front and what you all might expect in the future for periodic refreshments if we are able to get the work that we want to do funded. Okay, so first thing first is the release of that data set so that folks can start to leverage it. So I'll just call it the Wind Toolkit LED for simplicity. No, it stands for long-term ensemble data set. So the first thing that my colleagues always want me to say is that folks may recall the original Wind Toolkit. It was covered the historical weather years 2007 to 2013. There was that extension into 2014 over the continental United States at relatively high resolution. All of those parameters may or may not necessarily apply to the updated Wind Toolkit LED. So for the 3 historical years, 2018 to 2020, we have that 2-kilometer, 5-minute data over CONUS as well as Alaska and Hawaii. However, there is also a second data set, the North American Climate Data Set, that covers 20 years from 2001 to 2020, but at lower resolution, both temporally and spatially. And also importantly, the historical Wind Toolkit, we released those power forecasts based on a few power curves of sort of then current wind turbine technology. That is not part of the data set this time, and there is not the same sort of validation effort that was released with the last Wind Toolkit. That said, it's available online. It's not the same as the old data set, but we do hope that it's useful to some of the folks in this room, and we know it'll be useful to us at NREL. So this is kind of what I was saying, but they're not power forecasts this time, and it is important to recall that these different data sets are at slightly different temporal and spatial resolution, as well as the number of historical years that they cover, right? So we have this higher resolution data set, but it's just for those 3 weather years, unless we get a handful of more supercomputer runs spun up. And then there is also a third data set, that's the offshore data set. So that is at higher resolution, but of course, covers the offshore space as opposed to over the continental United States. This is available online, so folks can sort of get the slides and come back to this. There are both a number of visualizations online. So these are kind of like the maps. And then there's also the actual data, which is available at this website, as well as through AWS. So we hope that that can be integrated with folks' tooling in similar ways to what happened historically with the Wind Toolkit. Again, with all of the exceptions of how things are maybe a little different this time. Uncertainty estimates are included in some of Carolina and her colleagues' work, but there is not a full validation for grid applications. And every time I press on this, they put little notes in their work. Maybe they wouldn't want me to say this, where they do things like say, Luke, a priori validation is required. You're going to have to do it yourself. So you should just know that there hasn't been kind of the same effort that there was last time to look really closely at the power curves, translating wind speeds into wind generation, and going through the whole effort, sort of looking at the mean absolute error and some of these other metrics bias that folks tend to like in all different parts of the country. That said, you can get some of those uncertainty estimates from the wind speed, based on the work model that underlies what's been done by the team up at the Flatiron site. That said, so me and my team on the grid side, we have been working on some ongoing validation efforts so that we can try to integrate this data alongside some of the other data sets that have been talked about today in our grid integration work, right? As folks may know, some data gets released with the REED's capacity expansion model and some of our other tooling efforts. And there is an ongoing effort to kind of make the Wind Toolkit LED, as well as some other data sets available with those releases to cover more recent weather years, as well as just sort of more extensive data sets. So this is kind of like a high level overview of what we currently do at NREL and sort of what may come out in the future in the next sort of year or two as we do efforts to update our data and validate some of this stuff, right? So folks will see sort of towards the bottom left that historically there's that old Wind Toolkit data that covers the weather years 2007 to 13. And then our data science team, I guess you guys will hear from Grant Buster and some of those folks a little later, has done some great work to sort of integrate the HER data, which sort of, as Justin and John were discussing, has kind of changed in some ways over time and is more of an operational data set, but nevertheless covers in some manner the years sort of mid-2014 up through 2021. Then we have that Wind Toolkit long-term ensemble data set. So that's covering those 3 weather years, 2018 to 2020. And what we can do on the grid side is kind of compare some of this against the Energy Information Administration data. So that's that EIA 930 data set for folks who work closer to the grid side that has generation observations by regions of the country on an hourly basis since sort of mid-2018 or so. So we can take some of that data, there's some overlap, and we can start to do some comparisons of how well are these wind speed data when translated via power curve, tons of exceptions that we'll talk about, and issues, sort of how do they compare to what we're seeing in the observational data. So we'll talk just briefly here about a validation effort our team has undertaken for 2019 to 2020, right? So we start with that synthetic wind speed data from the HER and also from the Wind Toolkit LED. The data science team has their Rev tool that allows us to translate into wind generation. You can go from the wind generation to sort of map to the existing wind sites in the country, which we have as part of our tooling, right? Because we can only compare to where we have historical observational data that's going to be included in EIA 930. So, fortunately, there are a lot of system operators who have a lot of wind these days, as folks in the room know. And then we can kind of have time series plots and other metrics that compare the power output across each of these geographic areas, often ISOs like PJM and New York Independent System Operator. And we can see how that compares to the modeled wind generation, right? So we have this observational data, even if it's somewhat coarse. We've passed the wind generation. We've applied it to all these different sites. We've aggregated up, and we can do some time series comparisons of the HER data, the Wind Toolkit LED, and the observational data, at least for a handful of years at hourly resolution. Tons of caveats apply or sort of concerns. The way that I think of this is our team is making an effort to do an apples to apples comparison, but at best, I would say we're comparing different varieties of apples But as long as there's some folks in the room who like Honeycrisp and some folks who like Granny Smith, maybe we can do okay. So with that said, I would say that what we're kind of seeing is there is, correlation with reality, or at least with observational data in both the Wind Toolkit LED, and our team has done some bias corrections to the HER data, and that sort of makes it map to reality even more closely than without those bias corrections. That said, there's a number of caveats about sort of how well this apples to apples comparison can be done. In the interest of time, I'll leave sort of folks who are interested in the time series plots to kind of look back at the slide. That said, the one high level point that I want to make is that, just so folks are aware and are keeping track of this, is that we do tend to see these higher wind capacity factors in the Wind Toolkit LED. So this figure comes from our data science team, and you can kind of see on the top right there that the darker blue is higher capacity factors. And if you just kind of scan across the screen, at least what stands out to me is that in that middle part of the country, which is where the really high sort of capacity factor wind resource tends to be, that you're seeing these 50–55% plus capacity factors with sort of typical turbine vintages over that middle part of the country, just natively using the available Wind Toolkit LED data. And that struck us on the grid side as a little bit high. That said, the other thing that we've kind of looked at is just the correlation. So this is using the Pearson's correlation coefficient just for a year of data across some of those system operators, like MESO and ERCOT and SPP that have gigawatts of wind generation at this point. And we do see that both the Wind Toolkit LED there in the orange, and then also our bias correction to the HER data, are showing pretty high correlation with reality on an hour-by-hour basis. By reality, again, I mean observed data from existing wind farms. And it does tend to be a little bit higher in the bias correction to the HER data, but both data sets, in our view, are showing at least some utility for grid applications, looking out into the future and doing things like running capacity expansion models. That said, these validation efforts are ongoing and incomplete. And as Justin and other folks were gesturing at, it's just really hard to say what the gold standard is here. And I think that's some of what we hope to talk with folks about at the workshop, so that we try to do what's most useful for making sure that these data sets are useful in y'all's work. So with that said, we'd love to have folks weigh in via a survey that we also ran at our workshop in March. And that is what we will talk about sort of briefly and next, right? So we had this workshop a few months ago where a number of folks in the room, as well as many others, showed up to the Flatiron site, which is sort of up between Golden and Boulder for those who know that area out in Colorado. And we got lots of great input, and we hope to get a little bit more great input at this workshop so that we can try to make all this stuff as useful as possible. I want to just say like 2 or 3 things about what we learned at the workshop, and then I'll tee it up for you guys to offer your thoughts. So one thing that really came out for me in the sort of couple dozen responses that we got before the workshop is that in the wind data space, there are many more data sets that are commonly used than in the solar data space, where maybe there's a bias in who shows up to an NREL workshop, but the NSRDB is seems to be popular and commonly used in the field for grid applications. Whereas folks were talking about the HER, we've already heard about the ERA5, the Wind Toolkit. So there's just not as common of a standard for wind, which makes it a little bit harder to say, to sort of address all of the different issues that Justin was bringing up. That said, we tried to get folks to rank what they think is important for future data sets. And basically folks just said, make it more accurate, however you do it, like we'd love that. Obviously folks care about a number of different things. Validation is important, climate change is important, but there's just a number of concerns here about both validation and, at least from my perspective as someone on the grid side, how sort of synchronous these data sets are across wind, solar. Load is something that not only is influenced by temperature, but could be sort of more influenced by temperature in the future if you get things like electrification of space heating, and that drives peak loads in the winter. I mean, these things are just becoming more important, and having consistency across those data sets seems paramount. I would say that at least what I was seeing when we did some whiteboarding at the workshop is kind of 5 key focus areas that will inform our work and next steps at NREL. So people said that these data sets aren't really validated. We don't know what the metrics are for usability. What are the use cases? Like I was saying earlier, there's not this link across solar, wind, and load data sets that makes them as synchronous as we would like. So those are some of kind of the things that stood out to me when we did whiteboarding at the workshop. So with that said, we do still have this survey up and available. I'm going to try to, I think, finish out the little conclusion to the talk, and then I'll bring this slide back up if anyone wants to copy down the link and sort of help us out. Definitely the 15+ responses we got at the workshop have informed what we're thinking about doing here in the next year. And anything else that we hear from you all will influence what the NREL team tries to achieve to make these data sets as sort of readily accessible and usable as possible for the applications that folks in this room have. So I'll just briefly say what our next steps are, and then we'll try to close it out. So like I said, we're sort of continue to take feedback both on the new Wind Toolkit and what we can do to better validate and make data sets available to the community. So I know that one thing that my team sort of more towards the grid side is working on right now is this validation effort, right? What are appropriate use cases? What do those tail events that we care about for resource adequacy look like? You know, we've been having some conversations with the Telos folks and some of the other folks probably in this room about sort of what can we do to make that data available and as validated as we can, given sort of time and budget constraints. Combine that with the solar and load data sets that we have available at NREL. You know, historically, we've released stuff alongside reads. We expect to continue to do that in the future, but there are a number of caveats, some of which Justin already brought up, about sort of the spatial and temporal resolution in these models and how sort of synchronized with reality they are, especially in places that have complex topography or mixes of distributed generation. I guess we were talking about the Bay Area, things like that. I'm going to just say that you all should obviously stay for Grant's talk. You're already here. It'll be in about 40 minutes. But we definitely are trying to address some of these concerns about climate variability and how the future will be different from the past. And then the other thing that we just heard a lot from folks at the workshop, but maybe doesn't fall quite as straightforwardly within the purview of at least what we tend to do at NREL, is that having these comprehensive industry data sets. We heard earlier about some of the meteorological towers. One thing I was observing on that plot is it looked like maybe there aren't too many in California, and we have concerns about the ones in the Columbia Gorge, and it's like those are pretty big places for wind resource in the West. So sort of having more of these data available and kind of what can this community do to push folks to make that data both readily accessible and usable by power systems modelers who want to validate, but also for there to be sort of more of it and to make it usable. That's definitely something we are thinking about and heard a lot from our workshop participants. So with that said, I mean, definitely thanks to folks. And I will, let's see, it's 119 it looks like. So I'll leave this up. And if anyone wants to copy down the link, they should definitely feel free. And we will take your responses into account and look forward to talking with folks over the next couple of days. Thanks again.
Hey, thank you, Luke. And we are right on time, and we won't make the coffee break in about 20 minutes. So we will move on to the final presentation of the first session, which is historical and forward-looking data sets. And the presenter will be Cameron Bracken, who is an earth scientist at PNNL. Cameron.
There we go. All right. Hello, everyone. I also have to admit I am a stand-in also. Casey Burleson gave a similar talk at a previous ESIG meeting, and he wasn't able to make it today. So I added some stuff to his talk, and that's what you get. All right. Oh, it just started. Okay, so I'm going to just start with some motivation, which I don't think any of these points are really controversial at all. The existing grid is weather sensitive. That shouldn't be controversial at all. Weather characteristics, especially extreme events, are changing, and the grid is also changing rapidly. And all of these things will be a bigger concern under a decarbonized or a high renewable grid. So keep these in mind for the rest of the talk, but I don't think any of that should be very controversial to this group. So I'm going to keep hammering on some of these points throughout the talk. To assess the resilience and reliability of the bulk power system, it's critical to evaluate the performance with coincident data. We heard a couple people talk about this already today. I'm really glad that that is a term that is not that we're not the only ones using. And you also need to evaluate things across a wide range of historical and projected weather conditions. And today I'm going to be talking about data sets that we have available at PNNL. There are others that people have talked about that can help to do this. So what is coincident data? Coincident data is, well, one definition is it's derived from a single climate model. So you take a climate model, you process it into some sort of meteorological data, which is input to component models that are of specific interest to power system folks, such as load, wind, solar, hydro, there's probably others, and you get useful data for your power system models out of that. As opposed to non-coincident data, in which you might derive each of these different data sets from different climate models or different observational data sets, which have their own biases, or maybe some other sort of machine learned product, something like that. But the key is that when you have non-coincident data, you may miss a lot of things, such as temporal consistency. In a coincident data set, there are no mismatches in dates or times. This is particularly critical when you're looking at, I'll talk about this more later, but if you're looking at compound extreme events, for example, you want to know that these events are happening at the same time that occur across different variables. There's physical consistency in coincident data. That means you have uniform physical assumptions because they came from the same model. There might be biases in your coincident data, but when there are biases, they align across variables and then you can correct for them in a uniform way. And there's consistent statistical properties throughout the whole historical record. And then finally, the spatial consistency, which is primarily the variables, when you look at them spatially, maintain the correct spatial correlations. So I'm going to be talking about several different data sets that we have available at PNNL. They're looking at meteorology, load, wind, solar, and hydro, and a couple derived data sets from there that can help with more specific applications. All the data we have available is open source, it's vetted, it's available in multiple formats, and we're specifically developed all this data as part of this GoDeep project, which you can see the little tag for up at the top, which was a PNNL internal investment in support of targeted questions by the industry. So first of all, I want to talk about the meteorology data, which underpins all of these coincident data sets that we have available. You may have heard about this before. It's called the thermodynamic global warming data. It's not the same as a regular climate or meteorological data set, but it has some particular uses for the energy system, which are particularly nice for energy system applications. What it is a downscaled ERA 5, so at 12 kilometers. And so it has a 40-year historical record that is then repeated in the future. And so this comes with some downsides, but it also comes with some really amazing benefits, such that you can look at the exact event that occurred in the past, and you can look at it in the future, and the difference in the future period is we've applied some warming signal to it. So you can look at how the exact same event in the past, which you may already know how that stressed your system, you can look at how much worse that will be in a warming climate. And the different colored lines are different levels of warming, which are derived from collections of CMIT models that we group into these 4 groups. Sorry, and those 40 years are replayed again out to 2100. So just an example of what that would look like. In the historical period, there's a heat wave. There's going to be some other slides that focus on this same heat wave event in July 2018. You can directly see just at that snapshot in time how much worse the larger spatial event, larger spatial extent of that exact same event. So the first set of data that we have that's derived from this thermodynamic global warming data is load data, and it's produced from this model called the total electric load model. It's a machine learning model that produces load, energy demand at different scales. So we have it at the county scale, which I'm showing here, also at the balancing authority scale and at the state scale, which are all consistent with each other. Here's an example of what that load data looks like during that same event. Oh, this is actually not the same event, but this is in June 2019. Okay, I think you get the idea, but you can see that you can replay events and get this really nice picture of how the load was behaving. The next data set that a couple of data sets that we have are wind and solar. I've grouped these together. These come in a couple flavors. The first is point or plant data. They're not really points, but think of them as points. We've modeled, we've mined all the attributes of all the available EIA plants. So that's every plant that is above 1 megawatt about. And we've modeled the exact attributes of the plant to the best that we could and produced a long historical record for all of these plants. So it is synthetic record, but for a plant that maybe doesn't have a long record or the data is not publicly available, you can have a long historical record, 40 years, and we have future projections for these plants as well. We also have companion gridded data, which is using the same thermodynamic global warming data, and we assume, sort of like NREL's when Toolkit, the previous one, where they actually produced power generation at the grid cells, we assume that there is a hypothetical plant, wind or solar plant at a grid cell location, and then we model what the power generation would be at that grid cell. This is really nice data for, looking at what the potential of a plant at that location would be if there's not already one there. Oh, and that gridded data is also available in the future period. The next set of data is hydropower data. This is brand new. We actually haven't even minted the data, so this is like a sneak peek that it's getting published really soon, and we're working on a publication also. But we have modeled with a distributed hydrologic model every plant that we possibly could in the continental US, and we run that through a routing and water management model. So we have weekly and monthly power generation at all of these hydropower plants for the historical record. We're working on the future period as well. And then what we do is, using a post-processing step, we determine reasonable min and max power constraints for every time step in the data set, which is what I'm showing in the bottom right. And this is the kind of information that production cost models are able to ingest and use, this sort of constraints and energy targets. So this hydropower data set is PCM ready, 1,500 plants approximately. Yeah. I'm going to skip this in the interest of time. Okay, so having all of these load, wind, solar, and hydro data sets, well, hydro is not shown in here, but because it wasn't ready at the time, but we can get this really holistic view of what's happening during a particular event in the historical record or in the future period by combining all of these data sets, and we can be confident that since they're all coincident, that there's nothing misaligned and everything is apples to apples. So this is that historical event that I mentioned, and then the dashed line on top is that future period. So we can look at directly the effects on load, wind, solar, and hydro would be here too during these exact events and under certain amounts of warming conditions. Oh, and we also have prices, which I didn't mention, and unserved load, because all of this has gone through an energy system production cost model. Moving on to some other applications of this coincident data that we've recently worked on. The one is this National Transmission Planning Study, which is focused on stress events for the grid. They used particular events that they knew were stressful to the grid, particular heat wave events in the past, in I think 2015 and 2018. But using our coincident data sets and that TGW methodology, they're able to replay those exact events under warming conditions, and holistically using all of the data that I mentioned, get a really nice picture of what future stress might be. This report is coming out soon. The next application I want to talk about is extreme events. So everyone's aware of just regular extreme events. That's like heavy, flooding or heat waves. There are other classes of extreme events, though, where you have two types of extremes happening at the same time. This is called a compound extreme event. There's also sequential extreme events, which is two happening back to back. All of these have been recorded to happen in the US, and they're only getting more common. So for an example of what we can do in terms of those compound extreme events, we have a paper that came out late last year on compound wind and solar drought events. So because we have that coincident data, we can do some analysis on when wind and solar are both low, that would be a drought event. And we can classify that for different regions. These are balancing authority regions. We can quantify the frequency and magnitude and duration of all of these events. And this helps to understand transmission needs and possibly battery storage or other storage. Another example of this energy drought is a paper we're working on now, which isn't quite ready yet, but it's looking at how these compound energy droughts change in the future. And one really robust signal that we see coming out of this work is that we expect that just as we build out renewables on the grid, the severity of these energy droughts is going to increase. And that signal is really robust. It's just a matter of how much in a particular balancing authority or region. All right, so there are a number of practices with this coincident data that I've mentioned, some of which are better than others. And for example, using data that may or may not be coincident to test a limited number of specific historical events. That's good. Even better than that is testing a wide range of historical events with as long a record as you possibly can get your hands on. Even better than that is if all of those were coincident and derived from the same data set, same underlying data source. And something I haven't mentioned yet, even better than that is if you have multiple sets of coincident data so that you can actually get a handle on the biases of a particular data set. I'm glad that this ESIG report has been mentioned already because it mentions a lot of the things that I've talked about, and particularly this coincident data. Finally, how do you get access to this data? Well, it's a one-stop shop, godeep.pnnl.gov with 3 E's. That stands for Grid Operations, Decarbonization, and Environmental Equity Platform. I want to just reiterate that these data sets are open source, free. They've been vetted. Many of them have publications already or in the works. And they're available in multiple formats, and they're specifically targeted at being useful for the industry. Just some final messages. I hope I made it clear about this need for coincident data. This is critical, but also the need for coincident data across a wide range of historical and projected conditions. These conditions that stress the system now are definitely not going to be the ones that stress the system in the future, or if they are, they may be exacerbated. It's important to consider compound extreme events as well as isolated extreme events and sequential events. And I talked to you about some of the work that we've done using these data sets, and please, we want this data to be useful. So if you have any questions, please just feel free to contact me or go to the website.
Hey, thank you, Cameron. And we're right at 10 in time for the break. So as we did previously, started with session 2 for the morning. And the first half of this session will be on approaches of forward-looking data sets. And our first presentation will be by Robert Arthur, who's a staff scientist at Lawrence Livermore National Lab. And the title is the Energy Exascale Earth System Model. So, Robert?
All right, hi everyone. This is my first eSig workshop, so I really appreciate the invitation. I'm speaking today on behalf of the project team that I'm leading. It's an internally funded research project at Livermore focused on climate impacts on renewable energy. So I'm leading a multidisciplinary team that includes climate scientists, Chris Golaz and Shanghai Li, as well as energy infrastructure modelers, Jessica Wirt, Tom Edmonds, Matthew Signoroti, and JP Watson. So a brief outline of my talk. I'll start with an overview of the E3SM model, the basics of the model and how it works. And then I'll get into some detail of the different configurations that are available, the different data sets that are out there and the ones that we're planning. And then I'll transition at the end towards some applications that we're working on specifically for my project, specifically model evaluation for wind and solar resource assessment, and some climate-informed capacity expansion planning at the end. So E3SM is the US Department of Energy's global climate model. It's a fully coupled Earth system model, so it's physics-based, and it has leaders and contributors across the DOE national labs. You can see in the figure on the right that it's a coupled model that includes all these different modules for different Earth system processes, such as the atmosphere, ocean, land, etc. And these all are working together. In this particular talk, I'll focus mostly on the atmosphere model and weather variables of interest for energy infrastructure planning. A little more about E3SM. It's included in the global climate model ensembles or assessments that you've heard referenced in previous talks, including the CMIP6, and then that goes into the IPCC reports on climate change. What I want to focus on today with my talk is that E3SM, among the many climate models out there, has relatively unique high-resolution capabilities, and Livermore is leveraging those for energy infrastructure applications. I'll try to explain that in a bit more detail. So I'll start with an overview of the available E3SM configurations, which are listed here on the left. Sort of the standard model setup is a global model with 1 degree resolution in the atmosphere. That amounts to about 100 kilometers over the United States. You can see on the right here what the terrain looks like at 100 kilometers. Kind of on the other side, the very high resolution side, we have a model in development called SCREAM. That's the simple cloud resolving E3SM atmosphere model. And it's meant to run on exascale architectures at 3 kilometer global resolution. So that model is under development, and I'll show some statistics or some information on it on the next slide. As kind of an in-between to those relatively standard global model setup and the very high resolution global model setup, we have what's called the regionally refined mesh or RRM capability, and that allows us to selectively refine the grid in a region of interest. So we have two setups that I'll talk about today. One is a 25-kilometer North America RRM. So it has the 100-kilometer global model, and then it's refined, as you can see in the globe on the bottom left, over the continental United States and the surrounding area. So that improves both the representation of the terrain, as you can see on the right, as well as the associated meteorological variables. In a similar setup, but with a more focused domain, we have the California RRM. So that also has the 100-kilometer standard global resolution, but it's refined down to 3 kilometers specifically over California. So that's sort of approaching these high-resolution numerical weather prediction model resolutions that we've heard about in previous talks. In the terrain here, it's just kind of nice to see, sort of as you've seen before, in the 100 kilometers, California is relatively flat. But at 3 kilometers, you can start to see the mountain features, the Central Valley, the separation between the coastal regions and the mountainous regions. So that has effects primarily on wind, but also on other variables. So I included this chart mostly for people to reference at the end of available model configurations. But I'll talk through it a little bit just to give a flavor of what's out there. So the standard model on the left has the most data availability, both historical and future simulations. The future simulations are for an upper moderate emission scenario. That's the SSP 370. It has different output frequencies depending on the variable. And the references are down here, and all of these references at the end will have additional information about data availability. So I'd refer you there for additional details. But specifically for the released versions of the model, this link here will send you to the data sets in different formats, different output frequencies, etc. All right, so for the very high resolution global SCREAM model, as I said, it's more under development, but we have a recent publication coming out soon. It's in preprint right now. But we've done 4 seasonal runs for present day scenarios. They're each 40 days to show how the model performs in different seasons. Those have 3-hour output availability. So now, as I said, I want to focus here on the regionally refined mesh capability because I think it has a lot of potential for energy infrastructure applications. So the 25-kilometer North America model has only historical output right now at that same monthly, daily, and 3-hour availability, data availability. But for my project specifically, we reran the final 5 years of that case with hourly output. So I'll show some of that data next. And the same link, you can find information about the North America refined model. The California regionally refined model was run for a tangential project to mine, specifically for climate resilience applications. So it was run in these 5-year periods spanning roughly the present day to the end of century. And all of that data is hourly output. The future scenarios use the most extreme emission scenario. That's the SSP 585. And this reference, Zhang et al. Recently came out showing the details of that model and some preliminary analysis with it. So just to expand a little more on the benefits of the E3SM RRM capability, I think it really facilitates customized climate simulations for energy infrastructure applications. And we're starting to try to do some of that on my project. So I think what it offers is a flexible configuration where you can balance grid resolution with the computational expense. For example, the 3-kilometer global model although it's designed for modern computing architectures, is still very computationally expensive. So this offers an alternative where you can focus your computation on a specific region. We're also working on methods to more easily define the refined area over any location of interest in addition to the ones I've already mentioned. One additional thing that people are starting to do in the climate science realm is what's called a storyline approach, where you simulate a notable event that occurred in the past, such as a heat wave, in a future climate state, to see how the evolution of that event would change, say, with increased emissions and increased surface warming. So this RRM setup really facilitates that type of analysis for a specific region. And finally, there's no need for a separate regional downscaling model. So all of the refinement happens within one model. And I think really my vision, or our vision, for working with users on this type of model is that we can collaborate to run simulations for specific scenarios of interest over specific regions of interest. So I'd love to talk to anyone about that for the rest of the workshop. All right, so now I'm going to transition to some of the applications that I'm working on and my team is working on as part of this project. So first, we're evaluating E3SM for renewable resource assessment with the idea that present-day model evaluation will provide guidance for future simulations. Basically, we want to trust that the model can capture present-day dynamics before we start trying to project into the future. So we're evaluating E3SM using two data sets. First is the EIA production data from existing utility scale wind and solar installations. So contrary to what Luke mentioned, we're using the plant-specific data, which is monthly as opposed to hourly. That's Form 923. And once we publish this work, we're also hoping to release our processing scripts and the quality controlled EIA data set so that other modelers can use this data set for evaluation and update it as more EIA data becomes available. In addition to the realistic reported data from the EIA, we're also comparing E3SM to what I'll call benchmark model data sets, so the NREL Wind Toolkit and the National Solar Radiation Database. For now, we're using the original Wind Toolkit, but maybe we can update that in the near future. So I'm going to focus our evaluation for now on the North America regionally refined model, because we wanted to look at variability across the United States, not just in California. So here I'm showing multi-year average comparisons of E3SM, the 25-kilometer North America model versus EIA data for wind on the left and solar on the right. So each dot you see is an existing site, and they're colored by how well E3SM matches the EIA data. So white is within plus or minus 20%, and roughly 70 to 80% of the dots on these images fall within that white category. Red is an overestimate greater than 20%, while blue is an underestimate of that same magnitude. So we can see that overall E3SM is performing pretty well. We were quite happy with this when we saw it originally, because E3SM wasn't necessarily designed to forecast renewables. So while it's performing well for now, we're also looking into this variability and how we might improve it, especially the darker blue and red dots. So that was the EIA comparison. Now I'll show a brief comparison with the NREL models. So again, we have wind on the left, solar on the right. So I'm showing average capacity factor statistics, also multi-year comparisons. So the boxes indicate, sorry, the boxes indicate the first quartile, median, and third quartile. So you can see that the general seasonal trends are captured by E3SM. There's some variability between the models, especially for wind. For example, E3SM has generally higher wind capacity factors in the winter and lower in the summer. So that's something we're continuing to look into, as is likely a function of the model resolution. Again, this is 25 kilometers for E3SM versus single-digit kilometer resolution for the NREL model. So I think these results are promising, but we're continuing to look into this evaluation. So finally, I kind of want to pull everything together. The ultimate goal of this project is to use E3SM for climate-informed capacity expansion planning. So just kind of an overview of what we're doing here. We'll feed the climate model data set. In this case, we're looking specifically at California. So we're using the California RRM with the CATS grid model shown on the right. So that's an open representation of the California grid. So we pass that climate model data into a renewable generation model. We're using the NREL system advisor model, SAM. And we also pass it into an internally developed demand model. Then we feed those results into a stochastic capacity expansion model that performs optimization over multiple representative days that capture seasonal variability. And then we also include economic scenarios from the NREL annual technology baseline. So we're looking at different cost predictions for basically how much it will cost to develop offshore wind in California. And ultimately, we're trying to look at different scenarios for how much offshore wind can be built in California under these different constraints, including the future climate. So I have a backup slide with some more details on this if anyone is interested, and I'm happy to talk more. But for now, I'll just summarize by saying, again, that I think E3SM has unique high-resolution capabilities, and my team and others at LLNL are trying to leverage those for energy infrastructure applications. The regionally refined model version of E3SM, I think, really facilitates customized climate simulations for given scenarios and locations of interest. So I'm looking forward to partnering with different organizations to work on those simulations in the future. And I just gave some highlights of our ongoing applications, including evaluations of E3SM relative to reported EIA data, as well as those benchmark models from NREL, and then tied it all together with the climate-informed capacity expansion planning. So I'll thank you for your time and happy to take any questions now or for the rest of the workshop.
Hey, thank you very much. And we do have a time for a question or two. Does anybody have a question? Yes, come to the mic, please. Lacey's there.
Yeah.
Yeah.
I got it.
Thank you.
Yeah, it's less of a question, more of like curious about, you mentioned your self-developed demand model. Just if we have time, can you please elaborate a little bit? I'm curious about that. Thank you.
Yeah, so that was part of a separate project, but I can tell you some details, and offline I could tell you more. So it's California specific, and it uses load data that's aggregated at the utility level from California. So like PG&E for Northern California, and then the other utility regions.
So then how do you blend your weather or earth model inputs into there, or is it separate?
Basically, it takes temperature as an input and gives load as an output, I think. Yeah.
Okay. Any other questions? Okay, I think we'll move on. We'll have time for further discussion at the end of this session. So thank you. Our next presentation will be by Grant Buster, who's data scientist at the National Renewable Energy Laboratory. And the title of the talk is the Sup3rCC Dataset.
Can you hear me? Cool. Will this go? Or do I have to- Okay. Thank you. Hey everyone, my name is Grant Buster. I'm a data scientist at NREL, the National Renewable Energy Lab, and I'm going to be talking about some of our weather and climate data at NREL. So at NREL, we do a lot of really big renewable energy integration studies. Seminal studies like the NREL SEAM study, which Josh led, big continental studies like NERIS, the North American Renewable Integration Study, others that are more weather specific, like the evolving role of extreme weather events with high levels of renewables. I think Josh is going to touch on some of these in more detail in a little bit. And most recently, the National Transmission Planning Study, which we worked with PNNL on. These studies all try and envision the future of the electricity grid. How could a future grid operate with very high levels of renewables, around the year 2050? How do we get to net zero? The ironic part is that a lot of them, pretty much all of them, use historical weather data. So we're simulating future grids in 2050 with weather data from 2010. So how is that weather data used in the analysis? We typically use the NSRDB Wind Toolkit, which is here on the top left, and we convert that in a weather to power model. We use this model called REV, and we use historical load data. So measured or simulated energy demand. And then we simulate the power system, do capacity expansion to understand how a future grid might look, run production cost modeling to understand how it might operate, et cetera, et cetera. What I'm going to be talking about today is really how do we integrate new climate change data into this system? How do we, what kind of data sets do we need to simulate this future grid with future weather? So there's a lot of climate change data available out there. They're basically all available via these global climate models. E3SM is a global climate model. And CMIP6 is kind of the archive of all these different scenarios and projections of climate change. And every climate model has a different climate sensitivity, carbon emission sensitivity, and you can get a wide range of understanding of what the future of our climate might look like. Now, these are all typically very low resolution, typically around 100-kilometer daily average. So Justin was talking about how 30 kilometers is trash. Well, 100 kilometers is like really, really, really coarse. And daily average also, I mean, it's really hard to understand how power system operations work if you're doing only daily average analysis. So we want to bridge this gap, create data that's on the order of 2 to 4 kilometers in hourly resolution to understand power system operations with climate change impacts. There's a number of ways to do this. It's all typically called downscaling, physical model downscaling, statistical model downscaling. We at NREL are pioneering this new method called super resolution for renewable energy resource data with climate change impacts. Quite a mouthful, or just Sup3rCC for short. It's a super resolution model influenced by generative machine learning models for image and video processing. So what's happening here is we have this low resolution data here on the bottom left, and it feeds into a generative model. You can kind of think of it like ChatGPT getting a prompt, and it produces this really high resolution realization here on the right-hand side that's basically indistinguishable from the quote-unquote true high resolution, which in this case is a numerical weather model here on the top left. We like this approach because it's pretty unique in a few different aspects. It's really computationally efficient, 1 to 2 orders of magnitude faster than traditional numerical weather modeling. That means it's in practical terms, if you're doing like, a large wharf run, it could take many months to a year, maybe even multiple years to get all these runs done. If you want to run 40 years with Sup3rCC, you could get that done in a week. If you have a new year that you want to study with a specific event, You could get that done in 30 minutes wall time, have that plugged into power systems models within 1 working day. So really fast. It's designed for renewables, so we've designed these models and trained them specifically for wind, solar, temperature, humidity, and we're building out a precipitation model right now. All the outputs are fully integrated into our energy analysis software, all the open source software that NREL releases. So if you go to that GitHub, it's all open source. There's instructions on how to use this data and use it in Rev and other open source models at NREL. This computer can't handle the fun videos I have. Sorry. Okay, cool. So this is what the full data set looks like. We've released 90 years of data from 2 climate models from 2015 to 2059, weather years 2015 to 2059. We released it for all of CONUS. It's 4-kilometer hourly data, which you can see here on the right. And we have a journal article just published in Nature Energy describing the data, the methods, and a lot of validation, all these fancy plots, joint distributions and whatnot, showing that the data appears to be spatiotemporally coincident. So we have these weather patterns that move across space and time in a reasonable manner. And we have coherence across multiple variables, similar to previously used data sets and historical observations. Once again, the data set's public. It's on NREL HPC, which might not be useful to all of you. But it's also on ODI. So we serve it on AWS S3, and there are we deploy this using a data service where you can actually stream small parts of the data to your local laptop without paying a dime. We've started looking at how this kind of data, how climate change impacts influence energy demand. So here we're comparing historical weather from 2007 through 2013 against future weather, simulated weather from 2050 to 2059, and looking at changes in summer AC load and winter heating load. And generally, perhaps unsurprisingly, you can see large-scale changes, increases in peak summer AC load. It's going to be a little bit hotter. And generally large-scale decreases in peak winter heating load, although there are some cold events that are affecting the northwest. This is just for heating load. When you back this out and look at all sector load, the changes are a little bit less dramatic. You still see large changes, generally large spread changes in peak summer total load, although the magnitudes are a little bit less than just the HVAC load. You do see some extreme events in some regions. Here you can see it in Arizona, where you actually see a 40% increase in peak winter load, which is kind of crazy. When I first saw this, I thought it was an error. We messed up the load model, et cetera, et cetera. Started looking into it. This is actually a result of this totally unprecedented heat wave happening in Arizona, simulated in this climate model in about 2050. So you're getting this severe heat wave in February that's about 20 degrees Fahrenheit hotter than the previous peak heat event in Arizona. So this is a good example of how climate change could really impact the way we think about shoulder seasons or typically low load periods. If Palo Verde was in an outage during that period, it could be a really significant event. This also serves to illustrate that while storyline approaches are really valuable, PGW is a really nice way to think about climate change. There really can be some unprecedented events that are not well reflected in the historical record. So Sup3rCC can be used to help study that. We're just spinning up this new project at NREL called PACES, Power Planning for Alignment of Climate and Energy Systems. So this is kind of the future of Sup3rCC, what we're going to be doing with it. So we're going to be expanding the record for Sup3rCC, integrating more scenarios, more climate models, more versions of possible futures. We're also going to be doing a companion data set with WRF, traditional numerical weather modeling, to compare and contrast, say, when can we use this generative ML? Where does it fail? When should you be using traditional numerical weather modeling for better precision? We're also going to be exploring planning strategies under climate uncertainty. So what do you actually do with all this data? You know, if I give you 10 versions of what 2050 could look like, how do you actually make decisions on that? We have some thoughts on how to do that, but we're going to be exploring this over the next 3 years. And then we're working with actual utilities, TVA and Southern, to make sure this work is actually useful. There are some known issues in Sup3rCC. So this is a figure from the paper. Number one is bias. You've been hearing about bias all day. The wind and solar, first, I should say, Sup3rCC is not a resource assessment data set. So if you want to know, like, where is the good solar data, if you want to know where's the good wind data, you should be looking at something like the Wind Toolkit or NSRDP. Sup3rCC is really to understand trajectories and climate change. As such, it has biases when you look at the historical data. It's kind of negatively biased versus Wind Toolkit, positively biased versus HER, a little bit positively biased versus NSRDB. Temperature is actually pretty right on. So this is something we're working on as part of the PACES project, is improving this. So we might release a doubly bias corrected version of the data next. There's also some imperfect diurnal cycles. When we're generating these diurnal cycles from daily average data, some of the wind data becomes a little bit noisy. You get some midday kind of local maxima that are not well represented in the Wind Toolkit or ERA. Timing of peak temperature can be off by an hour or two. This isn't totally uncommon stuff in other simulated data sets. It's just something to be aware of if you're going to use this data yourself. There's plenty of gaps in Sup3rCC. There's plenty of things Sup3rCC cannot represent. So hurricanes are not well represented. There's no wildfires. We don't have any sort of representation of population migration. And urban effects was also a big gap, the effect of local microclimates from the built environment. We have been working on urban effects, so I just want to quickly talk about that. We've been applying the super resolution process to an even finer scale. So we're going down to 500 meters in this case to actually resolve the effect the built environment has on the local microclimate. So here you can see ERA on the left-hand side, 31 kilometer over Los Angeles. And then on the right-hand side, you can see the super resolved urban heat island data at 500 meters. And you can actually see the effect of the built environment. Downtown LA is a little bit hotter. The area close to the coast is a little bit cooler. And we're training these models with really high resolution satellite observations as well as a network of point measurements. There was a very extreme heat wave in 2021 in the Pacific Northwest in Seattle. This actually presents a really great opportunity for validation and a nice natural experiment where you can take this event that's totally unprecedented in the training data and see how ERA represents this in the urban core, how ERA represents the urban microclimate, and then how the super resolved data does. And you see that in downtown Seattle near Capitol Hill, ERA 5 is underestimating the peak temperature by more than 2 degrees Celsius. So pretty significant underrepresentation of both the heat wave and the urban microclimate. The super resolved data actually matches it pretty well. We're overestimating by about 0.6 degrees Celsius at that peak hour. But generally, you can see the trend line matches almost exactly. You can also manipulate the albedo, the surface reflectivity, in the input of this data set. Albedo is a really big characterization of the urban, the built environment. There's been a lot of experiments specifically in Los Angeles on people actually painting streets white, for example, to reflect more sunlight to reduce the local temperature. You can actually manipulate the albedo fed into this model, and you can get the appropriate microclimate temperature response. So if you say, hey, we're going to paint the street white, the super resolution model is going to say, oh, that's going to cool the urban microclimate by this much. It actually matches up pretty well with previously reported values in the literature. So now we can actually simulate these unprecedented heat waves in the urban microclimate, understand their effects on cooling demand from residential building models. And we can also say, hey, if we paint all the roads white and apply cool roofs and do all these albedo interventions, how much does that actually reduce the temperature? And we can balance these two. So we did this study in ResTalk, and what you see is that the increase in cooling demand through mid-century, you have an increase in cooling demand by about 23%. There's a lot of uncertainty in that relative to uncertainty in climate change, but that's order of magnitude. That's kind of what you're looking at. From road albedo modifications, which is what they're doing in Los Angeles in a few different neighborhoods, you're painting about 15% of the area white. You're seeing about a 1 degree Celsius, maybe a fraction of a degree Celsius decrease in local temperature. That results in a 2% decrease in cooling demands. If you were to paint a lot more surfaces white and do all the houses, all the roofs white, you could get up, we estimate you could get up to about 6% reduction in cooling demands. If you were to install a cool roof on your roof, that impacts your local, your building cooling demand by about 11%. So if you combine these, if you take the local climate impacts and your actual building, your thermal envelope impacts, you can see a decrease, total decrease of around 17% decrease in cooling demand. It's not quite as extreme or not quite as big in magnitude as the increases in cooling required by increases in temperature. And there will certainly still be heat waves that will really stress your cooling demand, or if you don't have cooling, will really drive some dangerous indoor temperatures. But you can mitigate actually most of the stresses of climate change just through albedo modifications, both for the local climate and your thermal envelope. So pretty interesting results here. We're working on publishing this right now and putting it together. So hopefully see another super resolution for urban microclimate paper out there soon. That's all I have today. There's been a huge team that's helped in all this work at NREL and also colleagues at other national labs and whatnot. So just want to give a shout out to everyone. I don't think any of them are here today. So yeah, thanks to them. And yeah, thanks. Happy to maybe take a question. Yeah.
Thank you, Grant. We do have time for a question or two. Please come to the microphone. Lacey's coming to turn on the mic. Oh, there it is. Okay.
The slide which showed the 3 graphs in the Seattle region, can you please? Yeah. So the ERA 5, I think is under predicting for only in the mid-year part, right? For all of those, it's pretty consistent with observations. That's what this shows, right? So can you comment on how well what is that? Super UHI, right? How is it comparing? Because somewhere it is over predicting and somewhere it is ERA 5 is under predicting. So what what are the pros and cons of these two in these regions especially? Thank you.
Yeah, so in the 2021 heat wave was about a 3-day heat wave that you can see those 3 peaks in the middle, right? And ERA 5 is a very low resolution model. It does do some data observational simulation. But in some cities and in some events, it will underpredict your temperatures in the urban core. Because urban environments tend to trap heat, you get exacerbated temperatures. These effects aren't really well represented in the 30-kilometer ERA data. And so that's what you're seeing here, is that ERA is really underpredicting your temperature. So if you wanted to go study this event and study mortality effects, cooling effects, stuff like that, you would be underpredicting the effect of this heat wave if you were to use the ERA data. That's what we're saying here. In contrast, the super resolved UHI data matches it pretty well. You can see the nighttime temperatures are matched almost exactly. In that middle day, it overestimates, but it's actually pretty online with the other 2 days. it does a much better job of representing these extreme temperatures in this unprecedented event. So what I'm saying here is that we think this is a really good tool for understanding extreme temperature events in an urban core, some that are totally unprecedented, some temperature events that we've never seen before. Yeah.
Well, related to that, I have a question. How transportable are these models to areas where you might not have the data? So in some areas, Seattle, for example, you have a lot of data to train the model on the behavior of the Hebridean island. And you might go to other places where you don't have that data, or other parts of the world where there's very little data. Okay, so if we train the model where there's a lot of data,
Yeah.
how usable would it be in other situations?
That's a great question. So far, we've only demonstrated this for Los Angeles and Seattle as two kind of prototypical dense urban cores. Seattle because of this 2021 heat wave, and Los Angeles because of the albedo modification experiments. You know, we have plenty of satellite observational data for basically anywhere in the world now. The trick is local point measurements of air temperature. We pulled data from MADIS, which is a really kind of thorough data network, several data networks actually. If we didn't have a lot of that internationally, it'd be challenging. You at the very least need some way to validate your models. We could train, you know, using many different cities in the US and apply it to somewhere else, but at the very least, you need some observations to validate. Otherwise, you're flying blind. Thanks.
Well, thank you. And we'll move on to the next presentation, the final one on forward-looking datasets. And this will be given by David Larson, who is the technical leader in grid operations and planning at EPRI. And the title of the presentation is Creating Hourly Weather Time Series for Future Climates. David.
Great. Yeah, sounds like it's working. So hi, everyone. David Larson from EPRI, talking about how to create some future climate data sets at an hourly resolution. I'm going to be talking about a slightly different approach than what we've heard so far, but along similar use cases. Before I get into the details, I want to acknowledge the great work. This was really spearheaded by folks up here, especially Eric and Lavin. They're not able to attend this week, so I'm here presenting, but a lot of the work is really attributed to them. So one motivating example, and we've heard lots already, but just to reinforce, one motivating example might be resource adequacy. And in this, you're wanting to look about future systems, what are the risks on the supply and demand side, and you need hourly data, but you want that hourly data to also reflect future weather extremes. So you don't want to just purely go off of the historical record, because you want to see what might I face in 2050, those sort of situations. So, and this, again, other folks have mentioned this, but you have different options for this, and there's some pros and cons. So you really want these hourly resolution, forward-looking weather data sets. Global climate models, those are great, give you forward-looking data. They're daily resolution. They also have spatial resolution and limitations. You could interpolate the data. Some people do that. That's very simple and practical. And I think, as many of us know, sometimes the simplest and most practical thing is what people actually use. But you can miss important patterns that you want to pick up. Lastly, there's things like dynamic downscaling, which is very useful, tends to be expensive, and it's not widely available. And as we heard, there are other alternatives coming out. So different pros and cons. What we've been working on is a slightly different approach that we've been using fairly effectively in some projects. So the core idea of this is, why not combine the best of the two sides? Take all the great features of historical data and then match them with what you need from the climate projections. So historical data, you have the hourly resolution. It has that realistic variability, diurnal, seasonal effects, et cetera. You have all the variable links that you want. So that's great. It just doesn't have that forward-looking aspect. So then you take the pieces from climate projections. And so in this approach, what we're trying to say is there's already lots of great work on these climate models. we don't need to change that. We can take this great research and use it, but use it in a way that gets to what we need for a power system study. So the key steps of this, and I'm just going to kind of do the high level overview because I think for this meeting that's appropriate. So we take the historical data set. In these examples, I'll be talking about using ERA 5, though you could in theory use other historical data. You would detrend it, pretty standard approach. Then we would look at, from the climate models, we would look at the distribution of that data, and we would look at both their historical simulations compared to the projected period. So if you're looking, the last 20 years, and then you look at a projection going out to 2030. And so you look at the distributions there, and you look at the change in that. And then step 3, it's about applying that to the historical data to shift it. So in this way, very simple approach. It gets at it. It's well understood. I'm not going to be making any claims about is this better or worse than different models. There's some very interesting research aspects there. And it may be this is something that we use for now, but as other tools become more available, this becomes less necessary. But this has been useful for us, and it's been allowing us to do a lot of great work. Another thing I should mention here is this is all set up so you can use multiple climate models as input. If you have a favorite one you want to use, you can use it. If you want to do a full spread, that's also possible with this approach. So how much data does this generate? It's basically a function of how many years of historical data do you provide it, how many climate models, and then how many emission scenarios from there that you look at. So an example that we've done in some studies, you can get back 72 years of ERA 5 data. You can, for example, we've pulled 5 climate models from CMIP6, and then you can look at 2 emission scenarios. So that gives you 720 different years of potential weather data that you could use in your study. And so that's kind of the scale of, yes, it's a lot of data. It's not just to have a lot of data. It's then you can do probabilistic assessments or Monte Carlo. You want to have that large amount of data to look at different scenarios. What does it look like? Just an example for output. I want to make it very clear how this is really tied into, we want things that people can use. And I think that's true for all of us in this room, but just showing an example of this is what the output could look like in a very generic way, purposely shown this way because any tool could deal with this. It's a CSV file with a couple of columns. You can take that in whatever tool you want and it works. So that I think is a really attractive piece to this because I know in our experience at EPRI when we work with folks, everyone's very busy and the less friction you can introduce, the better. So if you just tell them, hey, it's a CSV file, any tool you want, you can read CSV, you're good to go. And just a standard naming convention that we're using based on the model and the scenario. But the point here is trying to keep it simple so people start using this, and then you can always make improvements, but this is already going to move people ahead. So I'm going to spend more time talking about some examples of this data just to show a few things. So what does it actually look like if you look at an hourly time series? So here we're showing, in this case, a couple of days from 2005 for a location. We have the historical data for this, the black line, and then each of the colors corresponds to effectively a different scenario that we generated. And you can see here that what we're capturing is we are getting from the daily climate models that temperature shift, but we're also still factoring in that diurnal shape and the natural variability. So this, again, that's kind of what we want in these studies. We want to see, well, this is what we're facing, but this is kind of, we're not just interpolating and seeing these massive changes that aren't realistic. Another part about this is the arrows to point to look at the two that you want to compare against. So the orange and green line, or however it's displaying there. So those, if you look at the distribution of the data set, if you take the climate model data compared to the synthetic projections, and you're still matching the distribution. And you're also starting to match and get that behavior you want out at the tails. So there's the little inlet plots for showing in the colder weather what's happening and how you're shifting more towards warmer, and then the hotter you're shifting out further. So it's matching that. And again, this is just one example, but you can do this with any type of model that you put as input. Another thing is then this also takes advantage because we're just using those existing climate models, you're capturing differences in the models. So you might have a model that is sort of quote colder. It's not showing as much of a heating change. So on the left is for one where you're seeing abnormally hot weather is only increasing by 2%. And then a warmer model is increasing by 7%, but same emissions scenario here. So you can factor that in. And that, I think, again, gives you that advantage of we're not telling you which one you have to use. It's you have maybe a preference, you go through, you want to do a different emission scenario, a different model, something new comes out, you can use that data with this approach. Another example, if you look at, for this example in 1980, just to give some numbers. So you look at the historical data from 1980 for this location. I believe this was Atlanta. And in the green, the first set of it, that's the spread of what the historical data showed. So in July, you actually saw 9 hours above 100 degrees Fahrenheit. In the yellow, the middle one, that's one of the versions from our method for kind of a lower emission scenario. And that's now showing 25 hours would be over 100 degrees Fahrenheit. And then if you go to a higher emission scenario, now you're seeing 34 hours above 100 degrees Fahrenheit. So this is just sort of reinforcing that point of it's picking up kind of the behavior you want. And you're also getting some numbers that are useful in the power system side to say, well, if I'm planning a system and I'm never really getting above 100 degrees Fahrenheit, but now suddenly I'm going to have, 34 hours, and that might be split across different days. It might be one period. That's going to change how you plan things. So I'll summarize this, and then there's a few extra things I want to talk about as some resources for folks. So from this, I think the key takeaway should be there's lots of reasons that we need hourly forward-looking data sets, as we heard from a lot of different folks today. This talk was specifically about a method about taking those climate model data sets that are daily resolution, combining them with historical hourly data to create realistic synthetic data. There's lots of benefits to this approach. One of them is it's simple, you can explain it, it's not a black box. It's also something that running this, the biggest part is just having access to the climate data and downloading that. Once you have that, this is a pretty simple Python script and you can run it very quickly. So again, focused on that practicality of you can start using this today. And I think that's where we're really seeing for a lot of folks of, if you can reduce the friction, that's how people start using this. And that's what we always need to keep in mind, as others have talked about today. But lots of great stuff here, lots of benefits. We've been using this. We're continuing using it in projects. There are some admittedly limitations for this. This is really focusing on creating data that's on a point specific. So you want to get it for a specific load center or city. A lot of our work has primarily focused on temperature. For different reasons, but the idea would you would use the historical, for example, solar radiance, and then you would only make this adjustment to the temperature. The other one is, while this does capture some of the extremes we want to see, you're not really going too far beyond the historical record. You are seeing some of the extremes, but you're not going very far beyond it. But again, if we haven't seen it before, that gets a little tricky of like, do you want to be showing these things, and how do you validate if that's going to happen? You can definitely talk to me about this stuff, but also a main contact for this would be Eric Smith, who some of you may know from our ESCA team. So just esmith@epri.com. So that's pretty simple. So want to mention real quick about a couple of related resources and then leave time for questions. So EPRI's got, this is a little bit of a plug, but I think it will be useful for this audience. So we've got a lot of R&D initiatives that come up. One of them is Climate Ready, that some of you may be aware of. And this is really thinking more holistically about how to factor in climate change to a lot of different things in the power system side. So if you're not involved with that, there's also lots of great resources. And the other one that just launched this year is the Load Forecasting Initiative, which is looking at both operational and long-term. And some of these same things are coming up here because you're wanting to do a long-term forecast and maybe factor in a forward-looking weather data set for that. So a couple of resources that folks can check out, again, in the hope of education. From Climate Ready, we've got a lot of great user's guide. That goes through a lot of key concepts, and that can be helpful for you or for others at your organization.
There's a data inventory. It's not a data set repository. It's more about here are different data sets and information so you can start going out and getting that data and start using it in your applications. And then the other one that's really great is Climate 101. Again, education about trying to get people up to speed in the power system side about some of these concepts and what they need to do and how they can talk with the relevant researchers. So lots of stuff available at epri.com/ready, might be of interest to a lot of folks here. And then the other thing I'll put up, and when we post the slides later, there's a couple of free reports that again are relevant. One is just a nice report that summarizes a lot of historical data sets, where they are, their characteristics, time resolution, locations, et cetera, weather, irradiance, wind, et cetera. So this is a nice one because we internally always would need to look up this information. So we thought, let's put this together and then also share it. And then another nice one, as some folks have mentioned about downscaling, that's a very powerful approach. This is a nice little overview of what are those key concepts, how are they kind of different or the same, and again, in the hope of kind of helping educate everyone. So I went through a lot of stuff very quickly, but happy to take any questions, and otherwise, thank you for your time.
Thank you, David. We have time for some questions.
Great.
Anybody have a question? Please come to the microphone.
Okay.
We have one here.
Maybe they'll turn on remotely. Okay, there we go.
Great presentation. Just the reports that you mentioned at the end there.
Yeah.
Are those public or are they just restricted to EPRI members?
Yeah, so these one in particular are public. You don't have to log in, anything, free to download. We've been trying to make a conscious effort of certain things of like, this is beneficial to everyone, so let's make them public. But yes, these two are public, and actually these items, they're public websites. So you can go there, start checking it out. You want to watch some YouTube videos, there you go.
Any other questions?
I guess I answered everything.
Very good. I do have one.
Yeah.
So one of the things you pointed out, that this is primarily for temperature, and of course the interrelation of load with solar and wind and hydro is very important. And so have you thought about those inconsistencies that might come up if you use NSRDB for solar, say, and use the wind toolkit for wind, and then you use this method for temperature, and you're not likely to get everything in sync on the hourly scale? How much of an issue could that be?
No, it's a great point about which data sets you're using. I think in this, what we've tried to be consistent on is if you use something like ERA5 and you use all the variables from ERA5, and then you just on the temperature from ERA5, you make that correction. Or if you use from a MET station, you have all those variables. I don't have an answer about how to resolve if you go from different sources. I think it's something you want to be conscious of and see, is it really affecting the result? But yeah, it's definitely something to watch out for.
Okay, thank you. Any other questions? We'll have time for more in a few minutes. So thank you, David. And we'll move on to the final presentation before the discussion. And Josh Wilczak from the NextEra Energy Resources, who is also the chair of the ESIT System Planning Working Group. And the presentation will be on a case study on using the data sets.
Great. All right. Thanks, everybody. Yeah, my name is Josh Wilczak. I'm the ESIG Systems Planning Working Group Chair. And what I want to talk about today is just from the Systems Planning Working Group, from kind of what we've seen through the systems planning community. How are we using some of these weather data sets? What might be, just to kind of give you a little bit more of the user's perspective on using some of these data sets that we've been talking about today, so that we can maybe try to come to maybe not a consensus, but some middle ground on kind of what type of resolution is needed. You know, how can we mix and match these without making Justin's head explode here. So what are some of the weather data and how are they used in weather data sets? So first and foremost, kind of wind and solar generation potential. This might seem obvious, but really it is kind of one of the first examples of really using hourly time synchronous weather data in power systems modeling. Debbie, I'm not sure if you ever thought you'd see another Western wind and solar integration slide here, but I do think this image is really important for what it did for kind of changing people's perspective on renewables. Really, this is all about, hey, if you look at the profile for a single site, for a PV site, it's going to look super variable because you are going to get cloud cover coming over all over the place. But the second that you start kind of looking beyond just your single site and looking regionally, you suddenly see some of that variability go away. This was something that was not well understood even a decade ago, I'd say, kind of more broadly in the power systems planning industry. So having this level of data just to kind of answer something simple like that was super useful not too long ago. So we're still using kind of hourly time synchronous data to answer questions about, hey, how do we dispatch the system? How do we commit the system? How does that commitment going to change in the future? I say forecasts are sometimes used too, but more commonly we are kind of interested in something just that looks like hourly, kind of a representation of what could be real time. Now, this is a little bit different than, if you're doing operations, you definitely want to look at forecasts. You want to understand kind of the probabilities of and how those might impact how you commit the system. But kind of when we're thinking like 10, 20-year planning, we're thinking of investments we're going to make in the transmission system. The forecasts become less important, I would say. And I'd say maybe a more recent change for kind of farther out future planning that has happened over the last few years is using weather data sets to better understand, when we might have turbine blade icing, when we might have snow cover on solar panels. I think this is still kind of ongoing research of capturing this well, but especially as you'll see later, this discussion of extreme weather climate impacts, kind of understanding some of the more kind of traditional infrastructure impacts from weather on wind and solar becomes more important as well. Load profiles. For a long time, we did not care about weather data sets. Obviously, load is heavily influenced by weather, but we were content to use historical load profiles and scale those by percentages to say, hey, we know that load is going to grow over the next decade by 1-2%. Maybe peak load grows a little bit faster than annual load. And we could use those in our planning models. Those days are definitely gone. The fact that electrification of many different end uses, from transportation to home heating and cooling, or building heating and cooling, data center growth, of course. These are things that we don't really have historical profiles to look back at and say, hey, we can just use this and scale it appropriately, because they change the profiles, which is what this plot here is showing. If you look at the low electrification, that's essentially kind of what today's profile would look like if we just scaled it, if we took a historical profile and just scaled it. But as we look towards medium and high electrification, not only are we seeing higher load growth on an average day throughout the seasons, but we're seeing a shift from summer peaking systems to winter peaking systems. And those winter peaking systems still kind of having this two-hump characteristic, but a particularly strong hump there in the early morning hours. So, if you're thinking of solving all of these things with just solar and batteries, that's a problem if, hey, you're just before sunrise and that's when your peak load is. So it's a change in the way that we're thinking there. Now, I will caveat this electrification statement by saying we know that load flexibility of all of these new end uses for electricity is going to be critical in maintaining adequacy and, honestly, the economic efficient operations of the system. So what we need from weather data sets is a base profile to start from. But if we get some things wrong, it's okay, because there is flexibility in the system and we need to be able to model that, and that has weather impacts, but it is not 100% correlated to the weather. There is other power systems operation considerations we have to take when thinking about the flexibility of that profile. But still really important that we're influencing those profiles based on weather. Now, increasingly as well, kind of a newer outcome over the last 5 years or so is the performance of other system components, mostly kind of thermal generators, in the face of different weather impacts. So on the left-hand side, you're seeing a plot of different types of thermal units, or just generators, not exclusively thermal in this case, and their forced outage rates as a function of temperature. This was some great work that Senator Murphy did about 5 years ago when he was a PhD student. Now he's at NREL, just kind of demonstrating that, hey, this idea that forced outage rates are constant throughout the year is way wrong. And if we're thinking about operating the system through really cold events or even really warm events, that we would have to take in the fact that we're not going to have the same amount of thermal generators online as we would have thought if we were just using the constant. Now, I think this is something we all know well after Winter Storm Uri, unfortunately, and the massive impacts that had to the ERCOT system. But 5 years ago, this was still quite novel, well before 2021. So increasingly, we're trying to catch up. I mean, I think the forcing function of Uri was pretty strong, but the kind of understanding of this impact was there. Finally, I've got being a little glib with the hydro here, calling it the unsynchronized synchronous machine. Obviously, hydro is heavily influenced by weather, but I might argue that it's one of the least important pieces to capture well. Most planners are content with modeling just kind of wet and dry sensitivities. And that's kind of demonstrated by the plot that I have here from a report that Justin and I put out back when I was at NREL, looking at a particular extreme weather event and the impact on what generation you dispatch during that event under some different hydro sensitivities. And by far, the largest impact to how you dispatch the system during this particular winter storm, this was in the Western Interconnection, was whether your hydro generation was flexible or not. That flexibility is hardly based on the weather data sets. There's lots of other constraints on hydro that influence how flexible it can operate from a power systems perspective, from fish and recreation to irrigation, that just have very little influence from the particular weather. Now, there's, I would say the biggest caveat here is the availability of hydro and the risks to the availability of hydro given climate change and warming and drying trend we're seeing is certainly something we should capture. So that's something that'll be quite important. And understanding the seasonal and interannual storage availability of that system. I'm now actually blanking on the year, but the heat dome in the Pacific Northwest that happened in June, most recently, they were actually able to operate okay through that because there were sufficient hydro resources during that time. Now, if that happened later in the season, after we had depleted some of the storage in the reservoirs, it might have been a little bit of a different case. And so this is just really a call for need to kind of understanding, hey, how much of a risk are we towards the end of summers in ensuring that we're maintaining some storage volume to respond to potentially even hotter and drier conditions. Okay, so now we're going to move a little bit. So those are kind of the overview of inputs into power systems modeling. I'm sure I've skipped over a few things. I'm sure I've made a few people mad about particular small things, but those are just kind of a few things that I've seen throughout the industry as a systems planning working group chair. So now I just kind of want to talk about kind of where things are going, and hopefully it's I don't think a lot of it will be new, but hopefully just kind of gives greater credence to working on some of the things that we've heard about today. So it's all about scenario planning, capturing extremes and capturing impacts of climate change. So kind of the equivalent in our industry of a Taylor Swift or Beyonce album drop was the FERC Order 1920 that came out a couple of weeks ago. Really, it will be, I do view this as a game changer for the industry. There's certainly plenty of regions that were already doing what FERC Order 920 is doing, but the fact that this kind of raises the bar for all areas that are under FERC jurisdiction. So really the main things that this has done is require multi-benefit planning. So this is looking across different, and the image I have here is from an ESIG report on multi-value transmission planning. So far I haven't seen like a good image come out to demonstrate what FERC Order 920 is, just a lot of legal language. Figured that wasn't super interesting to post here in a slide. Anyway, main things it's doing is requiring this multi-benefit planning, requiring a 20-year time horizon. So that requires weather data that we maybe takes into account the influence of climate change, certainly sufficient weather data to understand your resource adequacy risks as you're moving to more weather-dependent systems, as we've been talking about today. And then scenario planning is the other key aspect there of, hey, we're going to have to look at multiple different futures. It's not necessarily prescriptive of saying which futures you have to look at, but they need to be plausible. I mean, these could be things like, hey, a heavily distributed energy system, which, the weather data you need to model a distributed energy system relative to kind of a more large scale transmission build out system. That weather data might look quite different. You might be more focused on getting the solar right, more focused on getting the particular pockets of where you see a centralization of generation correct versus kind of a larger scale location where you really want to get correlations between regions better understood, since you're relying on your neighbors more in those situations. Big thing I should have hit on, like at the very top here for multi-benefit planning, is this requirement of understanding the resilience benefit of these systems to extreme weather events. So that, again, just hits on this requirement for needing to characterize extreme weather in a reasonable and correct manner. So to kind of lead in to discuss that a little bit more, I'm going to give an example of how we're starting to think about modeling extreme weather events in power systems planning. So again, kind of pulling from some work that Justin and I did, I'm going to tell a quick story on this tale of two cold waves and how those look different as we have these higher wind and solar generation futures. So what we typically see in a cold wave, especially cold waves that impact the eastern part of the United States, is that you have this cold come down the Rocky Mountains. And sorry, this is not an animated slide, but you'll have this cold come down the Rocky Mountains and with it kind of really high wind generation potential that sweeps across the system. But really the question about whether we can maintain adequate and reliable and efficient operations of the system during these times is what happens after that initial cold wave. So that's where we have two different versions of a cold wave here. On the left-hand side, the four maps that you see are from a February 2011 cold wave. This was kind of used as a comparison to Uri at the time that Uri happened, because it was quite cold in Texas and there were actual issues to the system operations during that time. And then another cold wave that did not make any kind of newsworthy impacts to the system, because it was, to use a word that Justin hates, mild in comparison to the extreme weather. But looking at the impacts it had to the wind system, the wind generation potential are quite different. The extreme cold wave tends to have wind generation available somewhere, even as it sweeps across the country. Not everywhere. You'll see on the February 3rd and 11th, there you see parts of Texas and Oklahoma where we plan to build lots of wind, have a pretty large wind generation lull. Red means low relative to what you would expect for that season. But in the northern parts of the country, we have actually strong wind generation potential. Whereas in the more mild cold wave, you kind of have a larger drought across the entire system. So this is the things that we have to worry about. We have to think about when we're planning and we're making our investment decisions. So just to talk through that a little bit more, these are dispatch stacks between those two cases, the 2011 cold wave on the left-hand side and the milder cold wave on the right. Just as in both cases, as that cold front is coming through, you have really high wind generation throughout the Eastern interconnection. Yes, I should have said these plots are dispatch stacks for the entire Eastern interconnection. So during that first couple of days, as the cold is moving through and load is increasing, about 80% of all generation in these modeled systems came from wind or solar. That's huge. I mean, we're seeing wind and solar penetrations in certain regions at this level, but this is the entire Eastern interconnection. But this is the days that follow that are the ones that we have to kind of think about a little bit more during these cold waves. So in the extreme cold wave, as you saw in the last map, there is, if we're able to efficiently exchange resources, not necessarily a copper plate, but more trade than we have today, Still 50% of the load is being able to be served by wind and solar in these cases. In the milder cold wave event, though, there are periods of very low wind and solar contribution. You're needing to ramp up your reserves. This could be a number of different things in these future systems. If we still have gas online, that could be gas. If this is long duration storage of some kind or hydrogen, this could be hydrogen, but something is needing to fill that gap during that period of drought. I'm going to kind of skip over that slide there, but really just kind of giving you a demonstration of how people are starting to think about modeling extreme weather and valuing different parts of the valuing different infrastructure for the multi-benefit purposes. So MESO is also, this is a presentation that Megan Pamperin gave during the last ESIG event, describing some of the kind of recent changes that they're making to their modeling as it relates to weather. So they are starting to incorporate in their LOLE studies the fact that you are getting increased outage risk at colder temperatures, just as we kind of talked about before. So this is becoming more important to use of weather data. In our ESIG resilience and transmission task force, we're also trying to look at like, hey, how do we make all of this weather data and impacts to the system available to more local planning considerations? So when an ISO RTO or a utility is doing their own systems planning, usually they have not just lower resolution of the weather outside of their not full, continental scale weather data sets that they have available, but they also don't have power systems data at a continental scale available for their planning purposes. So they need some kind of way to better understand, hey, if I'm going to be trading with my neighbor more, especially during extreme events, how can I, when I need to do my really detailed studies of my system, which already are quite taxing, how can I take information that is reasonable to understand how much I can rely on my neighbor? So that's some of the things that we're trying to get at here of understanding, hey, during extreme events, how correlated is your, let's say you're having an extreme in your region, how correlated is, how likely is it that your neighbor is going to have a similar kind of lack of available energy, whether that's from wind, solar, or thermals? And then what about your neighbor's neighbor? And being able to take that type of information to inform their planning studies to kind of try to simplify the process for them. Cameron already showed this slide, but I think it's kind of another good example of how power systems planners are evolving in in what they want to do with stress testing the system. And we are still kind of in that good range as Cameron and Casey had pointed out. This was a slide that Casey presented during the spring workshop as well. So I'm going to wrap up here with just a few quick thoughts. We've already seen the ESIG slide a few times from the report that Justin and the task force put out. But I might just provide a few quick thoughts. So for me, the most important pieces are of a weather data set for power systems planning is all about it being time synchronous. Now, John is definitely making me question my definition of time synchronous a little bit with how much mixing and matching of weather data sets that I use and whether they are truly time synchronous. But time synchronous, at least at a average hourly level, for me would be a really good place to start. I know that for some detailed studies, we want more resolved temporally, but I think we can make a lot of decisions with confidence with an average hourly time synchronization. Sufficient spatial resolution. Justin is also always making me question what that means for my purposes. But I do think, again, it kind of comes down to, hey, can we use the more spatial, the more resolved versions of these available for particular decisions, but when we kind of need to make broader planning decisions, can we come up with a less resolved version that we want? Probably the most important thing that I want right now is many weather years of data, that seems to be the biggest gap. Really cool to hear some of the things that Grant is doing with Sup3rCC, what the evolution of the wind toolkit, what PNNL has made available. So I think that there's lots of good things that I've both learned today and hopefully we can continue to build on. My last thought, though, that I do just want to provide everyone is there are many sources of uncertainty within our planning models, and weather data is hardly the only version of that. Now, I know that, hey, characterizing uncertainty in weather data sets is extremely hard, so I'm not necessarily asking, hey, I need an exact answer on that. But understanding that we're kind of bringing these in, like, as best we can characterize these while still enabling large infrastructure decisions to be made to progress the energy transition is really what we're after here. And so we definitely a question of making sure we're not making the enemy the perfect enemy of the good in this case. But that's obviously why we're here together, to better understand, you know, what is the right amount of resolution we need on all of our data sets. But great, with that, I'll turn it over to John.
Well, thank you, Josh.